Welcome, everyone. This is Chapter 6 of Théorie Horlogère, the authoritative Swiss horology theory curriculum, and we're opening what is genuinely the most mechanically rich and demanding subject in the entire course, escapements. Les échappements. If you've worked through chapters 1 through 5, you've already built a solid foundation in gear train geometry, mainspring mechanics, and oscillator theory. Chapter 6 is where every one of those subsystems converges, because the escapement is the single mechanism that bridges all of them. It sits at the interface between the driven gear train and the freely oscillating regulator, and it is the one component whose design most directly and immediately determines the precision of any mechanical timekeeper. Let me give you the full scope of what we'll cover. Section 6.1 establishes the fundamental definitions, traces the complete energy chain from mainspring to hands, and introduces the three-class classification system for all escapements in history. Section 6.2 performs a rigorous anatomical dissection of the Swiss lever assortment, 19 individually named components, examining each one's geometry and function in detail. Section 6.3 traces every microdegree of motion through the four kinematic phases of a single tick, with complete angular quantification. Section 6.4 covers the control and adjustment of escapement functions, plays, shocks, reversal, and stoppages. Section 6.5 analyzes the mixed layout geometry that makes the Swiss lever work. Section 6.6 quantifies power and efficiency at the escape wheel. And Section 6.7 presents the full taxonomy of alternative escapement architectures. This is the longest and most technically demanding chapter in the curriculum. Work through it carefully, take notes on the diagrams, and don't hesitate to rewatch any section. Let's get started. Let's begin with the most fundamental question: what does an escapement actually do? And the answer is not one thing, it is two simultaneous, inseparable, and equally essential functions that must be performed with perfect coordination on every single beat. Function 1: sustaining the oscillator. The escapement periodically injects small, precisely timed impulses of mechanical energy into the balance wheel, the regulating organ, to compensate for the energy the balance continuously loses to friction at its pivots and to air resistance as it swings. Without these periodic injections, the balance wheel would lose amplitude with every oscillation and stop completely within a matter of seconds. That sounds simple, but the engineering challenge is that these impulses must be delivered at exactly the right moment in the balance's cycle, in exactly the right direction, and in exactly the right quantity. Too much energy, and the balance overshoots its natural arc, distorting its frequency. Too little, and the amplitude decays toward stoppage. Function 2: counting and dividing time. The escapement releases the gear train, which is continuously driven by the mainspring, exactly one tooth at a time, in perfect synchrony with each half oscillation of the balance wheel. Every single tooth advance corresponds to exactly one tick or one tock. This is how the continuous, analog rotation of the mainspring is converted into the discrete, countable intervals we call seconds, minutes, and hours. The French textbook states it concisely: the escapement is an organe distributeur, a distribution organ, and it forms the critical mechanical bridge between the gear train and the regulating organ. Without the escapement, the hands would spin at random, uncontrolled speed. With it, every tooth released is a precisely measured quantum of time. To understand the escapement's architectural role with full precision, we need to trace the complete energy chain that runs through a mechanical watch from the mainspring all the way to the display. This chain has 6 distinct stages, each performing a specific transformation on the energy flowing through it. Stage 1: the energy source the energy. This is the mainspring, wound either manually by the crown or automatically by a rotor. The mainspring stores elastic potential energy proportional to its degree of winding, and it is the sole energy input to the entire system. Stage 2: the energy accumulator the energy. This is the barrel, le barrelet, the cylindrical housing that contains the mainspring. The barrel manages the torque profile delivered to the gear train, smoothing the sharp torque peak that would otherwise occur at full wind. Stage 3: the gear train transmission. This series of wheels and pinions reduces the barrel's slow rotation, typically one full turn every 6 to 8 hours, down to the high-frequency oscillation required at the escapement. The gear train also multiplies the rotational speed while transmitting torque, losing approximately 4 to 6% of power to friction at each mesh. Stage 4: the escapement distribution. This is highlighted in red in every textbook diagram for a reason. It is the critical control point of the entire system, the valve between the energy delivery chain and the frequency setting chain. Stage 5: the regulating organ or regulation, the balance wheel and hairspring, which define the oscillation frequency. Stage 6, the display, affichage, hands, digital indicators, complications. The escapement sits right at the most mechanically demanding point in this chain. It must both stop the gear train completely between beats, and drive the balance wheel during each beat. These are contradictory mechanical demands, and reconciling them with minimum disturbance to the oscillator is the central challenge of escapement design. Escapement design directly and profoundly determines the precision of any mechanical timekeeper, and understanding exactly why requires us to think carefully about what happens to the balance wheel on each interaction. Every single time the escapement makes contact with the balance wheel, every unlocking event, every impulse delivery, every relocking, it physically disturbs the oscillator. It changes the balance wheel's velocity profile, alters its energy state, and perturbs its natural frequency. If these disturbances were perfectly symmetric, perfectly timed, and perfectly consistent from beat to beat, they would produce no net error over time. But in reality, they are none of these things. They vary with mainspring tension, with temperature, with the position of the watch, and with the condition of the lubrication. These variations accumulate as rate errors. So the design question is, how do you minimize the disturbance, and how do you make whatever disturbance remains as consistent and symmetric as possible? Four engineering criteria have been established by the Swiss horological tradition to answer this question. Criterion 1, disturb the regulating organ as little as possible, for as short a duration as possible, during each interaction. Every microsecond the escapement is in contact with the balance is a microsecond of potential error. Criterion 2, deliver energy impulses symmetrically, equal amounts of energy before and after the balance wheel's equilibrium position, the dead point, point mort. Asymmetric impulse systematically biases the balance's frequency in one direction. Criterion 3, minimize mechanical friction and kinetic shock at every contact point, because every joule dissipated as heat or sound is energy stolen from the oscillator that must somehow be compensated. Criterion 4, provide reliable, absolute, and perfectly repeatable locking of the gear train between beats. If the escape wheel advances even 1 arc-minute more or less than intended, the counting function of the escapement is corrupted and the watch gains or loses time. These 4 criteria are the fundamental measuring stick against which every escapement in the history of horology has been evaluated, and every design choice in the Swiss lever traces back to satisfying or carefully trading off these mandates. All escapements ever designed are classified into one of 3 fundamental classes, and the classification criterion is singular and unambiguous. What happens to the regulating organ during the supplementary arc? The supplementary arc supplémentaire is defined as the portion of the oscillator's swing during which it is supposed to be completely free from any escapement contact. This is the ideal state, the balance swinging in total mechanical isolation, governed only by its own physical properties. Class 1, recoil escapements, échappements à recall. In these designs, the escape wheel is physically driven backward, it recoils, during the locking period, as the still swinging oscillator pushes back against the locked tooth. The verge escapement, échappement à verge, is the canonical example, used in European clocks from the 13th century onward. Class 2, frictional rest escapements, échappements à repos flottants. Here, a component that is directly linked to the oscillator remains in continuous sliding contact with the escape wheel throughout the rest period. The cylinder escapement, échappement à cylindre, is the defining example. The balance oscillates, but it is never free from escapement friction during any part of its swing. Class 3, free escapements, échappements libres. During the entire supplementary arc, both the escape wheel and the pallet fork are held completely at rest, and the balance oscillates with zero physical contact from either component. The Swiss lever escapement is the preeminent Class 3 design. Within Class 3, the detent escapement, the English lever, and the pin pallet also belong. The fundamental rule established by the textbook, Class 1 and Class 2 escapements disturb isochronism too severely for precision timekeeping. Only Class 3 free escapements can satisfy the 4 engineering criteria we just established. This is not a matter of historical preference, it is a consequence of physics. Let's examine the physics of why Class 1 and Class 2 escapements are fundamentally inadequate for precision timekeeping, because the argument is rooted in dynamics and deserves to be understood at that level. Consider the Class 1 recoil escapement first, the verge being the model. In this design, the teeth of the escape will press continuously against the pallet flags throughout the balance's swing. When the balance swings in one direction, a tooth on one side of the crown will drive the upper flag forward impulse. But as the balance continues swinging and overshoots, the opposite flag engages a tooth on the other side of the crown wheel and actually drives the wheel backward recoil. This means the balance wheel's own kinetic energy is being used to fight the gear train's forward rotation during every single beat. The restoring force acting on the balance, the force that determines its frequency, is not just the hairspring, as it should be. It is the hairspring minus the variable resistance force from the gear train, which changes continuously as the mainspring unwinds. The result, the balance wheel's effective restoring force, and therefore its frequency, varies continuously with the mainspring state of wind. Perfect isochronism is mathematically impossible. Now consider Class 2 frictional rest, the cylinder. Here the balance staff itself is the escapement element, and escape will teeth rest against the cylinder walls throughout the supplementary arc. This permanent sliding contact creates a continuous parasitic braking torque on the oscillator, a friction force proportional to the normal force from the tooth, which also varies with mainspring tension. Again, the oscillator's frequency is contaminated by the energy source's state of discharge. Neither class can isolate the oscillator from the driving mechanism. Only Class 3 achieves that isolation, which is the necessary precondition for precision timekeeping. This is why the Swiss lever, imperfect as it is, represents such a fundamental advance over everything that came before it. Here is the breakthrough achievement of the Class 3 free escapement, stated with full technical precision. During the supplementary arc, which represents the overwhelming majority of every oscillation cycle, typically 85 to 95% of the total swing, both the escape wheel and the pallet fork are held in a condition of complete, absolute, zero contact rest. Not near rest. Not minimal contact rest. Complete, absolute rest, with no friction, no recoil force, no variable braking torque, no physical connection whatsoever to the oscillating balance wheel. The balance swings in total mechanical isolation from the driving mechanism. Under these conditions, the only forces acting on the balance wheel are the restoring torque of its own hairspring, which is essentially constant for a given amplitude and temperature, and the extremely small damping force of air resistance, also essentially constant. No variable forces. No torque that changes with mainspring tension. No friction that varies with lubrication state. The balance wheel's oscillation frequency is therefore governed exclusively by two of its own physical properties: its moment of inertia, determined by its mass distribution, and the stiffness of its hairspring. These two parameters define the natural frequency of the oscillator with mathematical precision, and they do not change with the mainspring state of wind. This mechanical isolation is the foundation of precision. Every microsecond the balance spends in the supplementary arc is a microsecond of mathematically perfect isochronism. Conversely, every microsecond it spends in contact with the escapement during the lift angle is a microsecond of potential error. The entire design philosophy of the Swiss lever escapement, every geometric angle, every dimensional ratio, every material choice, is ultimately oriented toward a single goal: maximizing the duration and quality of this free supplementary arc, while minimizing the disturbance during the unavoidable contact phases. Now we enter section 6.2, the complete anatomical dissection of the Swiss lever assortment. This is the most detailed section of the chapter, and it requires careful attention to both the individual components and the geometric relationships between them. The word assortment is the formal technical term for the complete set of interacting parts that form the escapement mechanism. Before we examine each component individually, let's establish the macro architecture of the assortment as a whole, because understanding the overall system is essential context for understanding each part. The assortment has three primary subassemblies, stacked along a common vertical axis in the movement. Reading from top to bottom in the cross-section diagram, at the top of the stack sits the escape wheel, mounted on the escape pinion, the final pinion of the gear train. In the middle of the stack sits the pallet fork, pivoting on its own dedicated staff, the tige anchor. At the bottom sits the double roller assembly, pressed onto the balance staff, the axle of the balance wheel. These three subassemblies are kinematically coupled in a precise, rigid sequence. The escape wheel drives the pallet fork drives the roller assembly, and the roller, being integral with the balance staff, drives the balance wheel. On the return swing, the sequence partially reverses: the roller drives the fork, and the fork releases the escape wheel. The most critical architectural insight about the assortment, the insight that underpins every practical decision in escapement service, is this: every single dimension of every single part across all three subassemblies is mathematically interdependent, governed by standardized center distances called pointages. Changing the escape wheel radius forces a recalculation of the pallet fork arm lengths. Changing the pallet stone dimensions changes the effective impulse angle. Changing the roller diameter changes the impulse pin position and therefore the fork mouth geometry. It is one integrated kinematic system, not a collection of independent parts, and it must always be replaced, adjusted, and evaluated as such. The complete assortment of the Swiss lever escapement consists of 19 individually named components, and you must be fluent in both the English and French terminology for all of them, because both languages appear in technical specifications, service manuals, and examination questions. Let's go through the complete parts list systematically. On the escape wheel roue d'échappement, 4 named elements: the tooth, dent, which is the shaped projection that delivers impulse, the rim, surge, the outer ring connecting all teeth, the spoke, bras, the radial member connecting rim to hub, and the hub or center, moyeu, the central body mounted on the pinion. On the pallet fork anchor, 11 named elements: the fork body, baguette, the main structural member, the entry arm, bras d'entrée, carrying the entry stone, the exit arm, bras de sortie, carrying the exit stone, the entry pallet stone, pallet or levy d'entrée, the ruby that locks and releases on the entry side, the exit pallet stone, pallet or levy de sortie, on the exit side, the fork mouth, fourchette, the U-shaped slot engaging the impulse pin, the entry horn d'entrée, the guard flange on the entry side, the exit horn de sortie, on the exit side, the safety dart, the primary anti-reversal element, the entry banking pin, goupil de limitation d'entrée, limiting fork travel on the entry side, and the exit banking pin, goupil de limitation de sortie, on the exit side. On the roller assembly, 4 named elements: the large roller, grand plateau, carrying the impulse pin, the small roller, petit plateau, with the safety notch, the impulse pin, cheville de plateau, the ruby pin engaging the fork, and the safety notch, encoche, the cutout allowing dart passage. 19 components. Study both the plan view and the axial cross-section diagrams until you can identify each one instantly by sight. Component 1, the escape wheel roue d'échappement. Let's examine this component in full technical detail. The escape wheel is the last toothed wheel in the gear train, and it is riveted or pressed directly onto the escape pinion, the smallest and fastest spinning pinion in the movement. This direct mounting means the escape wheel rotates at the highest angular velocity of any wheel in the gear train, and its teeth must withstand repeated impact, sliding friction, and arrest forces at this elevated speed. The teeth of the Swiss lever escape will have a characteristic and immediately recognizable shape, the asymmetric talon or heel shape, dent talon. This shape is not arbitrary, it is the result of centuries of optimization for the specific kinematic requirements of the Swiss lever. Each tooth has precisely 4 functional geometric regions. Region 1, the locking face, plan de repose, spanning from point A to point B. This is the flat, highly polished surface that presses against the pallet stone's locking face during the rest phase. The tooth rests here, completely arrested, while the balance swings through its supplementary arc. The quality of this surface finish directly affects the friction coefficient and therefore the draw force and the risk of rest phase stoppage. Region 2, the impulse face, plan d'impulsion, spanning from point B to point C. This inclined surface slides against the pallet stone's impulse face during the impulse phase, and the interaction between these two inclined surfaces creates the driving force that pivots the pallet fork and ultimately energizes the balance wheel. The angle of inclination of this face determines how efficiently energy is transferred from the rotating wheel to the pivoting fork. Region 3, the locking tip, bec de repose, at point B. This is the critical corner between the locking face and the impulse face. It is the exact geometric point where locking occurs during tooth arrest, and where the tooth releases during unlocking. The geometry of this corner must be sharp, neither rounded nor bud, for correct kinematic behavior. Region 4, the impulse tip, bec d'impulsion, at point C, the corner at the end of the impulse face where contact between tooth and pallet stone definitively ends. In standard Swiss lever movements, the escape wheel advances approximately 10 degrees in 30 arc minutes per complete beat cycle, corresponding to precisely 1 full tooth pitch. With 15 teeth, the most common tooth count, the full wheel rotates 360 degrees in 15 beats, or 7.5 complete oscillations. Component 2, the pallet fork L-anchor. The name comes from the French word for anchor, which beautifully captures both the component's shape and its function. It anchors the gear train between beats and controls the precise timing of each release. The pallet fork is pivoted on its own dedicated pivot staff, tige de-anchor, and is typically pressed or friction fit onto this staff, as clearly shown in the cross-section diagram. This pressing creates a rigid, non-adjustable connection. The fork and staff rotate as a single body. The pallet fork is arguably the most geometrically complex single component in the entire assortment, because it must simultaneously perform 3 different functions with different geometric requirements. First, locking and releasing the escape wheel, via the 2 pallet stones that alternately arrest and release the teeth. Second, transmitting energy to and receiving energy from the balance wheel roller, via the fork mouth and horns. Third, resisting accidental displacement under shock, via the draw force acting on the pallet stones and the banking pin contact. The fork body, baguette, is the main structural member connecting the pallet stone arms to the fork mouth end. At the pallet stone end, two arms extend, the entry arm, bras d'entrée, carrying the entry pallet stone, and the exit arm, bras de sortie, carrying the exit pallet stone. At the opposite end, the baguette terminates in the fork mouth, fourchette, a precisely dimensioned U-shaped slot that engages the impulse pin on each active phase. Flanking the fork mouth are two guard horns, the entry horn, corne d'entrée, and the exit horn, corne de sortie. These horns are secondary safety elements that prevent the impulse pin from accidentally re-entering the fork from the wrong side, which would cause a reversal. Additionally, the fork body contains a small raised boss plot into which the safety dart is pressed or riveted. The total angular travel of the pallet fork from one banking pin to the other is approximately 10 to 15 degrees, a tiny rotation that must be reproduced with micrometer level precision on every beat, millions of times over the watch's service life. The third and final subassembly of the assortment is the double roller. Le double plateau, and it's the most intimate part of the mechanism, because it's the only component that physically connects the pallet fork to the balance wheel. Everything else pivots on its own fixed staff. But the double roller is pressed directly onto the balance staff, the same axle as the balance wheel itself, making them a single rigid unit. Looking at this slide, you can see the assembly clearly. Two discs, connected by a short cannon in the center, all pressed onto the balance staff. The upper, larger disc is the grand plateau, the large roller. It carries the impulse pin. The cheville de plateau, that little ruby pin set into the rim. That pin is the single physical contact point between the fork and the balance wheel. Every beat, the fork mouth reaches out, catches that pin, and either pushes it to deliver impulse or is pushed by it during unlocking. All the energy transfer happens at that one ruby point. The lower, smaller disc is the petit plateau, the small roller. Its job is safety. Cut into the edge of the small roller is the safety notch, the encoche. That precisely shaped cutout visible in the diagram. During the supplementary arc, when the balance swings freely, the safety dart on the pallet fork runs against the solid outer circumference of the small roller. This physically blocks the fork from accidentally rotating. The dart can only pass through the notch during the brief impulse phase, when the geometry is exactly right for a normal beat to occur. Typical materials are steel, brass, or glucider, a beryllium copper nickel alloy prized for being non-magnetic and corrosion resistant. One more detail, the impulse pin cross-section. The most common form is semicircular, as shown here, smooth entry and exit from the fork mouth. A triangular form also exists, which gives a sharper, more defined engagement. Both achieve the same function. So, grand plateau, petit plateau, cheville de plateau, encoche. For functional elements, one pressed assembly, all spinning as one body with the balance wheel. Now that we've walked through all three sub-assemblies, let's lock in the terminology. This slide gives you the bilingual nomenclature matrix, the complete parts list in both English and French, and you need to own both columns. In the Swiss horological tradition, French is the primary technical vocabulary, but English language service manuals and examination questions use both interchangeably. If you hesitate on either, you're working at a disadvantage. Let's run through the roller assembly terms with the full table in front of you. The entry banking pin is the goupil de limitation d'entrée, the pin on the entry side that limits how far the fork can travel. Its counterpart on the exit side is the goupil de limitation de sortie. Notice the structure, goupil for pin, delimitation for limiting, then d'entrée or de sortie for entry or exit. It's logical once you see the pattern. The large roller, grand plateau. Grand meaning large, plateau meaning disc. The small roller, petit plateau. The impulse pin, cheville de plateau. Cheville means pin or peg. The safety notch in coach simply means a notch or cutout. Here's my recommended study strategy. Don't try to memorize this as a list. Connect each term to its physical function. The cheville de plateau is the pin on the plateau that delivers the impulse. The encoche is the notch that lets the dart pass. The goupils de limitation are the pins that limit the fork travel. When terminology is anchored to function, it sticks permanently. A practical note: when you encounter a service manual that uses levee d'entrée for the entry pallet stone and another that uses pallet d'entrée, those are the same thing. The literature isn't always consistent, but your conceptual understanding should be solid enough that variations don't throw you off. Work through this table until every term in both columns is automatic. We've identified all 19 components. Now we need to understand the geometric framework that positions them relative to each other, and that framework is the pointage. A pointage has a very specific meaning in escapement engineering. It's the precise center-to-center distance between the pivot axes of the assortment components. Two distances define the system. O1 to O2, escape wheel. Center to pallet fork pivot. O2 to O3, pallet fork pivot to balance. Staff center. These two distances are the master dimensions from which every other dimension in the assortment is mathematically derived. The escape wheel pitch radius, the pallet stone lengths, the roller diameter, the impulse pin position, the fork mouth width, all calculated from the pointages. Change one distance, and the entire geometry must recalculate. This is why you cannot mix assortment parts from different pointage standards. A pallet fork designed for one pointage will produce incorrect drop angles, incorrect rest engagement, and incorrect play geometry if combined with an escape wheel from a different pointage. The assortment is one integrated kinematic system. Look at the two layout diagrams on this slide. The top shows the inline arrangement, disposition, and ligne droite, where O1, O2, and O3 all fall on a single straight line. Geometrically the simplest. Used in some historical pocket watch calibers. The bottom shows the angled arrangement, disposition angulaire, where the three centers form an angle alpha at the fork pivot, typically around 90 degrees. This is the standard in modern wristwatches because it gives the movement designer much greater freedom to position the balance wheel relative to the barrel and gear train. Standardized pointage values are codified in the NIHS standards. When you replace an assortment, you replace a matched set. We've established that the pallet fork travels only about 10 degrees from one banking position to the other, a tiny range, but it must be controlled with absolute precision. Too far in either direction and the mechanism jams or reverses. Two methods of limiting that travel exist, and this slide shows both. Method 1, banking walls, or autocoques. These are solid walls machined or milled directly into the main plate or pallet bridge. You can see them in the left diagram, two parallel walls forming a channel in which the fork body sits. The walls are integral to the plate material. They cannot shift or loosen. Their precision is set by the CNC machining of the plate, which in modern manufacturing holds to a few micrometers. The key advantage of autocoques: consistency and permanence. Once machined, they stay exactly where they are. The key limitation: non-adjustability. If drops are unequal or plays are out of spec, you can't fix it by moving the walls. A component must be replaced. Autocoques are the choice for modern high-volume production, where tight manufacturing tolerances make individual adjustment unnecessary. Method 2, banking pins, or goupils de limitation. Small cylindrical steel pins pressed into holes in the plate. Two pins, the inner pin G1 toward the center of the movement, and the outer pin G2 toward the edge. Right diagram shows this configuration. The critical advantage: adjustability. By pressing a pin deeper or shallower, or rotating a pin in a slightly off-center hole, the watchmaker can fine-tune the fork's travel range during a sheavage. This is invaluable for individual movement, finishing, and for any adjustment work where you need to equalize drops or correct play values. Banking pins for adjustment, adococks for production. Both achieve the same kinematic goal. We're moving into the geometry of pallet stone placement, one of the more subtle topics in the chapter. To understand why the standard solution works, we first need to understand why simpler solutions don't, starting with equidistant rest repose equidistance. The defining question in pallet stone layout: where, relative to the fork pivot, do you place the two pallet stones? Different geometric choices produce different kinematic consequences. Equidistant rest answers this by placing the locking tips, the becs de repose, of both pallet stones at equal distances from the fork pivot center. To verify, draw a circle centered on the fork pivot. If it passes exactly through both locking tips simultaneously, you have equidistant rest. The red circle on this slide illustrates exactly that. The consequence of this symmetry, the moment arm for the unlocking force, is identical on both entry and exit sides. The hairspring must push against the same angular resistance to unlock either pallet stone. Unlocking difficulty is perfectly equal on both sides. That's the advantage. But here's the problem. The stones have finite length. If the locking tips are equidistant, the midpoints of the impulse faces, where the tooth slides during impulse, are at different distances from the pivot. The exit side's impulse face midpoint sits at a longer moment arm than the entry side. This means the tooth pushes the fork harder on the exit alternation. The energy delivered to the balance is greater on one beat than the other. Asymmetric impulse. The balance is pushed harder every other beat. This creates a systematic isochronism error that accumulates into rate deviation over time. Equal unlocking, unequal impulse. Good geometry for one criterion, problematic for the other. We've covered all the components and the geometric architecture. Now we're ready to actually run the mechanism, to trace exactly what happens during each of the 4 phases of the escapement cycle. Let's start with phase 1, the rest phase. Repose. This is the most important phase for precision, and also the simplest in terms of what's happening mechanically, because essentially nothing is happening. And that's the whole point. Look at this diagram. The roller and balance wheel are swinging through there. Supplementary arc, the arc indicator shows the range of roughly 220 to 270 degrees of total balance rotation. The impulse pin is completely disconnected from the fork. It's out in the clear zone, well away from the fork mouth. The pallet fork, the anchor, is completely still. The baguette is pressed cleanly against the banking pin. You can see the 2 circles showing the 2 banking pin positions. The filled circle marks the active one. The fork isn't just sitting passively, it's being actively held there by the draw force. As long as the mainspring has energy, the escape wheel tooth presses against the pallet stone locking face, generating a torque that pulls the fork against its pin. And the escape wheel is completely arrested. One tooth is locked solidly against the locking face, plan de repose, of the active ruby pallet stone. The wheel doesn't drift or creep. It's frozen. This is the essence of Class 3 freedom. During this entire phase, roughly 93% of the complete cycle, the balance oscillates under the influence of its hairspring alone. No variable forces. No friction from escapement contact. The frequency is governed purely by the balance's moment of inertia and the hairspring stiffness. This is what the rest phase looks like. Deceptively quiet. Profoundly important. Here's the master reference table for everything that happens during one complete active cycle, the kinematic state space matrix, tableau de fonctions etc. Angles. 3 components across 4 phases, with a specific angular value for every intersection. The columns, roller on the left, fork in the middle, escape wheel on the right. The rows, repose, degagement, impulsion, sécurité. Rest phase, roller in the supplementary arc at 220 to 270 degrees, fork at rest. Wheel at rest. Everything still. Unlocking, the roller consumes approximately 8 degrees. The fork rotates 2 to 4 degrees. The wheel undergoes geometric recoil of 0 degrees 15 arc minutes, then dynamic recoil of 0 degrees 0 minutes 15 seconds. The escape wheel actually moves backward before it moves forward, not a malfunction, a geometric consequence we'll see in detail shortly. Impulse, the roller covers approximately 30 degrees, split symmetrically around the dead point 15 degrees before, 15 degrees after. The fork swings approximately 10 degrees, driven by the tooth against the pallet stone impulse face. The wheel advances approximately 10 degrees 30 arc minutes, 1 full tooth pitch. Safety, the roller resumes the supplementary arc. The fork travels the lost motion of 30 arc minutes to 1 degree under draw force, seating against the new banking pin. The wheel drops 1 to 2 degrees until the next tooth lands on the opposite locking face. Now focus on the 3 active phase roller angles, 8 degrees unlocking, 30 degrees impulse. These together define the total lift angle, the window during which the roller is in any contact with the fork. The remaining 220 to 270 degrees is the supplementary arc. The key insight here, those 30 degrees of roller impulse translate into just 10 degrees of fork rotation. The 3-to-1 ratio is the kinematic lever ratio of the assortment, built into the geometry of the center distances. The draw le tirage is the feature that makes the Swiss lever safe to wear on a wrist. Without it, any shock that disturbed the pallet fork could potentially stop the watch or cause a reversal. With it, the fork is actively and continuously pulled back into its safe rest position. Let's understand exactly how it works. Look at this diagram. There's a tooth pressing against the ruby pallet stones. Locking face. The force vector from that tooth is pointing in the direction shown by the large red arrow. Critically, that force is not directed through the fork pivot. It's offset. And that offset creates a moment of force about the fork pivot that rotates the fork toward the banking wall. Here's the elegant part: the energy driving this rotation comes from the mainspring itself. The mainspring drives the escape wheel forward. The tooth presses against the inclined locking face. The geometry of that inclination, the draw angle, converts the pressing force into a rotational torque on the fork, pulling it against the banking pin. The mainspring is literally being used to hold the fork in place. The more wound the mainspring, the stronger the draw. This is what the slide labels as the mechanism. The microscopic angle of the ruby's locking face uses the forward rotational torque of the escape wheel to physically pull the pallet fork tightly against the banking wall. And the result is clear: if the watch sustains an external shock, the inertial force on the fork tries to rotate it away from the banking pin. But the draw force counters this. As long as the draw force exceeds the inertial force, the fork stays where it belongs. The draw is why you can wear a mechanical watch while moving, exercising, or accidentally knocking your hand against a surface. Without it, every jolt would be a potential stoppage. We've completed part 1 of chapter 6, and this synthesis slide brings together the 3 core concepts we've established. First pillar, the mandate. The escapement must act as an energy distributor or gain distributor while leaving the regulating organ entirely undisturbed during its supplementary arc. Not just metering energy, not just counting beats, but doing both while protecting the oscillator's freedom. Every time the escapement touches the balance to deliver energy, it risks disturbing the very frequency it's trying to sustain. That tension between the two functions is the central design challenge. Second pillar, the assortment. A rigidly interdependent system of three subassemblies: escape wheel, pallet fork, and impulse roller locked to exact center distances called pointages. We've now identified all 19 named components across these three subassemblies, understood the tooth geometry and pallet stone geometry, and understood why dimensions can't be mixed between different pointage standards. Third pillar, what comes next? Part 2 takes us from static anatomical understanding into the dynamic. We're going to trace the microkinematics of each phase in real time: the unlocking phase, the impulse phase, the drop, the lost motion, with full angular quantification. We'll define the total lift angle, the virtual lift angle, the dead point, and the 6 key nodes in the roller cycle state space. If part 1 was what are the parts and how are they arranged, part 2 is what exactly happens to each part during each microsecond of the tick. Take a moment to review the 19 components and the 3 layout concepts before moving on. Part 2 builds directly on everything we've just covered. Welcome to Part 2, Functions and Angles of the Swiss Lever Escapement. This is Section 6.3 of Theory Horologère, and it's where the mechanism really comes alive. We move from anatomy to kinematics, from what the parts are to exactly what they do, when they do it, and by how many degrees. The key insight highlighted on this slide is worth reading carefully before we go further. All functions and angles are mathematically identical for both the entry pallet d'entrée and the exit pallet de sortie. The cycle is perfectly symmetric. This matters enormously for examination purposes. It means you only need to understand the cycle once. The entry alternation and the exit alternation run through the same 4 phases, with the same angular values, just on alternating sides. There's no separate entry version and exit version of the kinematic analysis, just one cycle that repeats. Part 2 covers 3 interconnected topics. First, a phase-by-phase kinematic breakdown of all 4 operational phases with complete angular quantification. Second, angular state-space mapping will define the complete coordinate system. That describes where the roller, fork, and wheel are at any moment during the cycle. Third, the vector physics of the draw mechanism, le tirage, which we've introduced conceptually and will now analyze in full geometric detail. By the end of Part 2, you'll be able to look at any position of the assortment and tell me exactly what phase it's in, what angle the roller has traveled, what angle the fork has moved, and what the wheel has done. That's the level of fluency this section builds. Let's start with the master matrix. This table, the kinematic state space matrix, is the complete reference document for the angular behavior of all 3 assortment components across all 4 phases. Study it carefully, because every number here represents a specific physical event. The columns represent the 3 moving subassemblies: roller on the left, fork in the middle, wheel on the right. The rows represent the 4 phases: repose, degagement, impulsion, sécurité. Rest phase, row 1. Roller, supplementary arc, 220 to 270 degrees. Fork, rest. Wheel, rest. Everything still. Unlocking, row 2. Roller, approximately 8 degrees. Fork, 2 to 4 degrees. Wheel, geometric recoil of 0 degrees 15 arc minutes, then dynamic recoil of 0 degrees 0 minutes 15 seconds. The escape will actually moves backward before advancing. We'll visualize the reason shortly. Impulse, row 3. Roller, approximately 30 degrees. Fork, approximately 10 degrees. Wheel, approximately 10 degrees 30 arc minutes. The roller travels 3 times farther than the fork. That's the mechanical leverage ratio of the assortment geometry. Safety, row 4. Roller, supplementary arc again, the balance is now freely swinging. Fork, lost motion of 30 arc minutes to 1 degree under draw force. Will drop of 1 to 2 degrees until the next tooth lands on the locking face. At the bottom, the definition of the dead point mort. This is the exact angular equilibrium position of the balance where it passes through zero. Velocity, the neutral axis between two alternations. The impulse is split symmetrically about this point, 15 degrees before, 15 degrees after. That symmetric split is the defining kinematic hallmark of the Swiss lever. Know this matrix cold. Let's go deep on phase 1, the rest phase. This slide presents it as a formal state space analysis. Each component's exact condition is specified and labeled. Starting with the roller, plateau. Status, disconnected. The impulse pin is far from the fork. The balance is swinging outward through the first part of its supplementary arc, currently moving away from the dead point with kinetic energy from the last impulse. The supplementary arc covers 220 to 270 degrees of total balance rotation. For reference, 270 degrees means the balance rotates 3/4 of a full turn in each direction. The fork anchor. Status, arrested. The baguette is pinned cleanly against the banking pin. Not resting loosely, actively held. The draw mechanism ensures continuous engagement. The escape wheel tooth pressing on the locking face generates a torque pulling the fork against the banking pin. The fork is in static equilibrium between draw force and banking pin contact. The escape wheel roue. Status, arrested. A single tooth is locked dead against the locking face plan de repose of the active ruby pallet stone. Under the full force of the mainspring torque transmitted through the gear train. The wheel cannot advance, cannot recede. Frozen. This state persists for the entire supplementary arc, approximately 90 to 93% of the total cycle time. In a watch beating at 4 Hz, the supplementary arc lasts about 0.11 seconds. The active phases together consume the remaining 7 to 10%. During this entire rest state, the balance wheel's frequency is determined purely by its own physical properties, moment of inertia and hairspring stiffness. Nothing from the escapement interferes. This is mathematically perfect isochronism, and it's the physical foundation of the Class 3 advantage. Phase 2, unlocking, degagement. The balance has swung to maximum amplitude and is now returning. As it descends back through the dead point, the impulse pin approaches the fork mouth from the correct direction and begins to enter it. The active cycle begins. Let's read the state of each component from this diagram. The impulse pin, cheval, enters the fork mouth, fourchette. Look at the curved arrows. The roller is rotating, driving the pin into the mouth opening. The pin contacts the inner wall of the fork mouth and begins pushing the fork. Fork action, the fork rotates 2 to 4 degrees. This is small but consequential. As the fork pivots, the active pallet stone, levee d'entrée, shown highlighted here, begins to slide laterally out from under the resting escape wheel tooth. Unlocking ends the precise instant the tooth reaches the locking tip, back to repose of the pallet stone. At that geometric moment, the tooth is no longer restrained. Roller action, the roller has consumed approximately 8 degrees from first contact to the moment the tooth is freed. The end condition, stated clearly on this slide, unlocking technically concludes the microsecond the tooth tip reaches the bec de repose of the stone. Not before, not after. And here's where the escape wheel does something surprising. It doesn't simply wait and then advance. During the fork rotation that frees the tooth, the geometry of the pallet stone rotating about the fork pivot actually pushes the tooth backward. The wheel recoils before advancing. We'll see the exact values on the next slide. Key numbers for this phase: 8 degrees on the roller, 2 to 4 degrees on the fork. These are the angular costs paid for each unlocking event before any energy is received in return. This slide reveals one of the most counterintuitive phenomena in the entire Escapement, recoil. And it happens in two distinct stages. Left diagram, geometric recoil, recul geometrique of exactly 0 degrees 15. Arc minutes, 1/4 of a degree. Here's why. The pallet stone is a rectangular block mounted on a fork arm that rotates about the fork pivot. When the fork rotates to free the tooth, the stone rotates with it. A rotating rectangle pushes outward as it turns, its corner describes a slightly larger arc than its face. This outward push acts directly on the tooth resting on the locking face, pushing it backward. The escape wheel physically reverses by 15 arc minutes before anything else happens. Right diagram, dynamic recoil, recul dynamique of 0 degrees 0 minutes 15 arc seconds. Much smaller, a factor of 60 less. When the geometric recoil decelerates the wheel to zero velocity, the wheel's own rotational inertia carries it fractionally further backward before the mainspring torque reverses the motion. This is the inertial overshoot. Combined total recoil, approximately 0 degrees 15 arc minutes 15 arc seconds. That's the wheel's position when it finally begins its forward acceleration. Why does this matter? Two reasons. First, it's the kinematic basis for understanding rest face stoppage, which we'll cover in section 6.4. At full wind, this recoil is largest, and if the draw angle is too steep, the friction during this recoil phase can exceed the hairspring's ability to complete the unlock. Second, it quantifies a real energy dissipation, some mainspring energy is consumed in this brief backward motion before the wheel moves forward. The kinematic summary box confirms phase 2 totals, roller angle approximately 8 degrees, fork rotation 2 to 4 degrees, will recoil minus 0 degrees 15 minutes. 15 seconds, immediately followed by forward acceleration. Phase 3 begins. This slide is the kinematic summary box for phase 2 unlocking, confirming everything we've just analyzed, and previewing the transition to phase 3. The three key measurements: roller angle consumed approximately 8 degrees. Fork rotation 2 to 4 degrees. Total wheel motion, minus 0 degrees 15 arc minutes 15 arc seconds, the combined geometric and dynamic recoil immediately followed by the initiation of forward angular acceleration. Focus on the transition statement at the bottom. In the next sub-millisecond, mainspring energy violently drives the wheel forward into phase 3. The moment the tooth clears the locking tip of the pallet stone, there is zero resistance to the escape wheel's forward motion. All the torque that the mainspring has been building throughout the entire rest phase is suddenly released. The tooth that was just freed is now clear. The opposite pallet stone is now directly in the wheel's path. The escape wheel accelerates forward under full mainspring torque, and the advancing tooth immediately contacts the impulse face of the opposite pallet stone. The locking tip bec de repose shown labeled on the diagram is the exact geometric moment of transition. Everything before it, phase 2, unlocking, cost without return. Everything after it, phase 3, impulse, energy delivery to the balance. Understanding this transition clearly is important for diagnosing escapement problems. If you can arrest the movement exactly at this point, with the tooth just at the pallet stone locking tip, you're at the zero energy boundary between the two phases. The slightest additional rotation of the balance either completes the unlock or fails to, depending on whether the system is correctly adjusted. Phase 3 begins now. Phase 3, impulse, impulsion. This is the energy delivery phase, and this diagram captures what's happening at the force level with 4 labeled steps. Step 1, mainspring torque stored in the wheel drives it forward. The escape wheel has been waiting through the entire rest phase, with one tooth locked and the full gear train torque building behind it. The moment the tooth is freed, this stored energy is released. The wheel accelerates forward. Step 2, the tooth's impulse face slides forcefully against the pallet stone. Impulse face. Two precisely inclined surfaces, the tooth face and the ruby Stone face makes sliding contact. The geometry of these angled surfaces converts the wheel's rotational motion into a lateral force on the pallet stone, which creates a torque about the fork pivot. Step 3. The pallet fork is violently pivoted. That torque rotates the fork from one banking position toward the other, sweeping through its total lift angle of approximately 10 degrees. Step 4. The fork mouth pushes against the impulse pin on the large roller, injecting kinetic energy into the balance wheel. The force impulsion L labeled in the diagram acts on the impulse pin, accelerating the balance to sustain its oscillation. The rotational torque shown, approximately 0.01 Nm 10 millinewton-meters. A tiny force by engineering standards, acting through a tiny angle, but precisely what the balance wheel needs. Notice the Swiss lever's contribution here. Both the tooth impulse face and the pallet stone impulse face contribute to the energy transfer. This is shared impulsion partigi, distributing wear and friction between two highly polished surfaces. This slide captures the defining kinematic achievement of the Swiss lever, the one property that distinguishes it from most historical predecessors: symmetric impulse delivery. Look at the diagram. Two positions of the impulse roller are shown, one before the dead point, one after. The dead point mort is marked by the dashed center line. Before the dead point, the roller has traveled exactly 15 degrees of impulse. After the dead point, it will travel exactly another 15 degrees. Total impulse arc, 30 degrees, perfectly divided about the equilibrium position. The angular symmetry readout confirms it, 30 degrees total impulse duration. Exactly 15 degrees before and 15 degrees after the dead point. Why does this symmetry matter so profoundly? The dead point is the balance wheel's equilibrium position, where the hairspring exerts zero net torque. If the impulse were delivered entirely on one side of the dead point, say, entirely during the approach, it would artificially accelerate the balance through its equilibrium, shortening the half period on that side. Systematic isochronism. Error: the balance runs at different rates on alternating half oscillations. But if the impulse is split exactly 15 and 15 degrees about the dead point, the effect is symmetric. Equal energy before and after the equilibrium. No net positional bias. The frequency is unaffected by the escapement's energy injection. This symmetric split is not accidental. It's a direct geometric consequence of the mixed layout, trace mixed, which we'll analyze in section 6.5. The center, distances, pallet stone positions, and fork geometry are all chosen so the dead point falls exactly at the midpoint of the impulse arc. This perfectly symmetrical energy delivery prevents the escapement from artificially speeding up or slowing down the balance, preserving isochronism. That's the key engineering insight of this slide. Phase 3 ends at a specific, geometrically defined moment, the moment of separation, le moment de la séparation. Look at the diagram. The tooth is sliding along the impulse face of the pallet stone. The balance and roller are at maximum velocity, the label is on the upper right. At a precise instant, the impulse tip of the tooth, bec d'impulsion, reaches the impulse tip of the pallet stone. These two tips align, and physical contact breaks. The tooth separates from the stone. The separation line, linea de separation, is the dashed line on the diagram. Everything before that line, tooth still in contact. The moment the geometry crosses it, contact is gone. At this instant, the tooth is no longer driving the fork. The fork is no longer driving the impulse pin. The balance wheel is traveling at its maximum angular velocity for this beat. All the energy the fork can deliver has been delivered. The transfer is complete. The balance wheel is now free. It enters the upward supplementary arc carrying maximum kinetic energy, which converts to potential energy in the hairspring as the balance decelerates, then back to kinetic energy on the return. Meanwhile, the escape wheel is suddenly free of pallet stone restraint. It's Continues forward under its own inertia, now with no contact with any stone. 4. A brief angular interval, the wheel is in free flight, this is the drop phase. Beginning. The slide states it cleanly, the impulse phase concludes the exact moment. Physical contact is broken between the tooth and the pallet stone's impulse face. And energy transfer is officially complete for this alternation. A clean mechanical boundary. Phase 3 over. Phase 4 begins. Phase 4 starts with the drop la chute. This diagram labels it explicitly as unrecoverable energy loss per d energy irrecuperable, and that honest label tells you exactly what you need to understand about it. Definition from the data readout: the drop is the angular freefall of the tooth from the end of impulse contact until it violently strikes the opposite pallet stone locking face. The angle, 1 to 2 degrees. During this free flight, the escape wheel accelerates forward under mainspring torque with nothing restraining it. A tooth in free fall. The kinetic energy it accumulates during this angular interval is exactly what gets dissipated as heat and sound when the tooth lands on the locking face of the opposite pallet stone. That's the drop shock, the loudest of the 5 mechanical shocks per cycle. Why must the drop exist? The geometric reality: at the moment the impulse tooth separates from the exit pallet stone's impulse tip, the next tooth is still approaching the entry pallet stone's locking face. There must be angular clearance between the end of one tooth's impulse and the landing of the next. If there were zero drop, the two contacts would overlap, the tooth finishing impulse would still be in contact with the exit stone as the next tooth tried to land on the entry stone. Conflict, jam, stoppage. Some drop is mandatory. The engineering question is, how much? Exactly as much as geometric necessity requires, and not 1 arc-minute more. Minimizing the chute is a primary goal in high-end escapement design, because every arc-minute of unnecessary drop is energy wasted as the loudest shock in the cycle. When you equalize entry and exit drops during a sheavage, you're optimizing this parameter, ensuring both sides waste the minimum necessary angular interval. After the drop, after the tooth has landed on the locking face of the opposite pallet stone, the escapement cycle isn't quite finished. There's one more small but critically important angular travel that must occur: lost motion, l'échappement. Purdue. Look at this diagram. The fork body, baguette, is shown in 2 positions, indicated by the red shaded region. Position 1, where the fork is when the new tooth lands on the locking face. Position 2, where the fork is after it has traveled to the new banking pin. The angular distance between these 2 positions is the lost motion angle omega of 30 arc-minutes to 1 degree. What drives this motion? The draw force. The moment the new tooth sits on the new locking face, the draw geometry activates immediately. The tooth pressing on the inclined locking face generates a torque pulling the fork toward the banking pin. The fork rotates this last small angle and seats firmly against the pin. Why is this critical? The safety mandate on this slide ensures the fork is fully locked out of the way before the impulse pin can possibly return. Without this margin, a fatal collision would occur. The balance wheel, after receiving impulse, is traveling outward on its supplementary arc. It will eventually return. When it does, the impulse pin will approach the fork mouth again. The lost motion ensures that by the time the pin returns, the fork is already firmly seated against its banking pin, not somewhere in transit between the drop position and the pin. The lost motion is the safety margin that guarantees the fork is in its correct stable rest position before the next active phase begins. With the completion of the lost motion, the cycle closes. The baguette is seated against the banking pin. The tooth is locked on the locking face. The balance wheel is swinging outward on its new supplementary arc. All 3 subassemblies are back in the rest state. 3 terminal events on this slide. First, sequence complete. The four-phase cycle has run from repose through degagement, impulsion, and sécurité, and has reset to repose. One complete beat has occurred. Second, maximum amplitude. The balance swings out to its maximum amplitude of 220 to 270 degrees, stops, and reverses direction. At maximum amplitude, all the kinetic energy from the impulse has been converted to potential energy in the wound hairspring. The balance is at zero velocity. Then the hairspring drives it back. Third, cycle reversal. Upon returning, the balance strikes the opposite side of the fork mouth on its descending arc, triggering phase 2 in reverse. The opposite pallet stone unlocks, the opposite side of the escape wheel advances. Impulse is delivered on the other alternation. The tock follows the tick. The large diagram shows the complete supplementary arc, 220 to 270 degrees. Indicated by the dashed arc and the escape wheel and balance wheel in their resting relationship. In a watch beating at 28,800 vibrations per hour, 4 Hz, this entire four-phase cycle repeats 4 times every second, 14,400 times per hour, over 300 million times in a 10-year service interval. The mechanism must perform identically on the 300 millionth beat as on the first. That requirement drives every single design decision in the assortment. Let's consolidate everything we've just traced into one master reference, the kinematic values matrix. This table gives you the total movement, unlocking angle, impulse angle, safety/lost motion, and recoil for each of the 3 components in one place. Roller, total movement approximately 38 degrees, the total lift angle, the complete angular window from first contact through the end of lost motion. Unlocking approximately 8 degrees. Impulse approximately 30 degrees. Recoil not applicable. Fork, total movement approximately 13 degrees. Unlocking 2 to 4 degrees. Impulse approximately 10 degrees. Lost motion 30 arc minutes to 1 degree. Escape wheel, total advance approximately 10 degrees 30 arc minutes, 1 full tooth pitch. During unlocking, the wheel doesn't advance, it recoils, minus 0 degrees 15 arc minutes 15 arc seconds. Impulse approximately 10 degrees 30 arc minutes. Drop 1 to 2 degrees. The synthesis statement at the bottom is worth focusing on. This matrix instantly translates the massive approximately 30-degree active balance swing into the microscopic approximately 10-degree internal fork and wheel interactions. That ratio, 30 degrees of roller motion producing 10 degrees of fork motion, is the physical exchange rate of the assortment. The balance makes large angular movements, the fork and wheel make small, precise ones. The assortment geometry is the mechanical translator between these two scales. Know this matrix. These numbers appear in examination questions, and they're the benchmarks against which you verify escapement function during achievage. Here is the fundamental design principle that unifies everything in escapement engineering, the horological rule: the greater the ratio of the supplementary arc to the lift angle, the higher the precision of the timekeeper. The slide illustrates this with 2 side-by-side diagrams. Left, the active system. The red wedge represents the lift angle, the small angular window during which the balance is in contact with the escapement. All parts move simultaneously. Isochronism is disturbed. Right, the passive system. The large blue sector represents the supplementary arc. The balance is entirely free. Escapement is locked securely. Isochronism is mathematically perfect. For the Swiss lever, a lift angle of around 38 degrees against a supplementary arc of 220 to 270 degrees gives a ratio of roughly 6 to 7 to 1. For every degree of lift angle, there are 6 or 7 degrees of free supplementary arc. That's quite good. For the detent escapement, which delivers impulse on only one alternation and has a nearly zero force unlocking mechanism, the ratio is even higher, directly explaining its superior precision. For the verge, the ratio approaches zero, there is no supplementary arc at all. Isochronism is continuously disturbed. Precision is fundamentally limited. This single ratio is the most important parameter in escapement design. Every engineering improvement in escapement history, from cylinder to lever to detent to modern silicon, can be understood as an attempt to increase it, either by reducing the lift angle or by increasing the quality and duration of the free arc. This diagram is the roller cycle statespace map diagram de l'angle de levy, and it gives a complete geometric picture of every angular position in the balance wheel cycle, mapped to the 6 key event nodes. 6 nodes define the state space, all labeled on the right side of the slide. Node A, start of total clearance, debut du dégagement total. The angular position where the impulse pin first makes any contact with the fork mouth wall. The very first moment of contact. The active cycle begins here. Node B, start of virtual clearance, debut du dégagement virtual. After initial contact, a brief interval takes up slack. B marks where substantive unlocking motion begins. Node C, start of impulse, debut de l'impulsion. The tooth has cleared the locking tip. The escape wheel is free. Energy delivery begins. Node M, the dead point mort. The exact angular equilibrium of the balance. Impulse is symmetric about this point, half before, half after. Node D, end of impulse, fin de l'impulsion. Contact between tooth impulse face and pallet stone impulse face breaks definitively. Drop phase begins. Node E, end of lost motion, fin du chemin perdu. The fork baguette has seated against the new banking pin. The balance is free again in the supplementary arc. Between E and the next A lies the entire supplementary arc, the lone, precise, free oscillation window. The arc from A to E is the total engagement angle de-engagement total. Phi. The arc from C to D, symmetric about M, is the impulse arc of approximately 30 degrees. This map is the complete angular coordinate system of the escapement. Know the 6 nodes, and you can describe any state of the mechanism precisely. This diagram brings together all the angular arcs of the roller cycle in one complete picture, with actual degree values from a calibrated example assortment. The central axis, the dashed vertical line, is the dead point mort. Everything is symmetric about this line. That bilateral symmetry is the geometric proof of the Swiss lever's symmetric energy delivery. Reading the arc dictionary on the left. AOB and DOE are the lost motion angles, chemin perdu, at each end of the active phase. They're equal, one on each side. AOC is the total clearance angle, the angular interval consumed by the unlocking phase, from first contact to the start of impulse. COD is the total impulse angle, approximately 30 degrees, split 15 and 15 about. The dead point M, com equals mod. AOE is the total lift angle, alpha, the complete engagement from first contact to end of lost motion. The specific values shown at 20.25 degrees, 22.97 degrees, 10.25 degrees, 7.31 degrees vary between different assortment sizes and designs. Don't try to memorize these specific numbers. What matters is the structure, the symmetric organization about the dead point, and the relationships between clearance angle, impulse angle, and lost motion. The conclusion: the Swiss lever is a triumph of symmetrical geometry, balancing the massive dynamic forces of a watch perfectly across a central axis. Every angular interval on the left of the dead point has a corresponding interval on the right. Bilateral symmetry about the balance's equilibrium position. We introduced the draw mechanism in part 1. Now let's analyze it with full engineering rigor, because understanding the draw at this level is essential for both examination preparation and practical adjustment work. The problem: external physical shocks to the wearer's wrist could cause the pallet fork to bounce inward, rotating away from its banking pin, and fatally collide with the balance wheel. Without a mechanism to prevent this, any sharp knock would potentially stop the watch or cause a reversal. The solution uses the geometry of the ruby locking face to convert the escape wheel's forward torque into a locking force on the fork. Here's the precise mechanism. The locking face is inclined at a specific angle, the draw angle, shown as alpha draw in this diagram. The escape wheel tooth presses against this inclined surface. Because the surface is inclined rather than perpendicular to the tooth's motion, the reaction force vector has a component that does not pass through the fork pivot. This off-axis component creates a moment about the fork pivot. The equilibrium equation on this slide, F-lock equals tau escape times R draw. The locking force equals the escape wheel torque times the draw geometry's moment. Arm. As long as F-locking exceeds F-shock, the fork stays in place. The mainspring's own energy is being used to actively hold the fork against the banking wall, with a force proportional to mainspring tension. The more wound the mainspring, the stronger the draw. This is why the draw angle specification includes a safety margin above the friction angle, to ensure adequate protection even at low power reserve. The draw angle is one of the most precisely specified parameters in the Swiss lever, and the calculation is slightly more complex than it first appears. Because there are two related definitions, and the entry and exit pallets have different values. This slide shows both pallets side by side. Left, entry pallet. Right, exit pallet. Both show the draw angle beta with its measurement geometry. Draw angle beta at the locking tip is defined as the angle between two lines. The perpendicular drawn from the locking tip to the line connecting the locking tip to the fork pivot, and the actual locking face surface of the pallet stone. This is the geometric inclination of the locking face. The mathematical relationships box gives you two definitions. Angle alpha, measured at the rest point to repose, the specific location. D on the locking face where the tooth tip actually rests during the quiescent phase. This gives a slightly different numerical value than beta because the rest point is not at the locking tip. Angle epsilon, the clearance angle. The asymmetry, LA symmetry, is critical. On the entry pallet, beta equals alpha plus epsilon. On the exit pallet, beta equals alpha minus epsilon. The entry pallet has a larger effective draw angle than the exit pallet by exactly the clearance angle epsilon. Why? Because the entry and exit pallets sit at different geometric positions relative to the fork pivot, and the unlocking geometry plays out differently on each side. The optimal range for alpha, 13 to 16 degrees. Well above the 9-degree minimum friction limit for steel on ruby. Below 16 degrees, where friction during unlocking becomes too large for the hairspring to overcome. This slide puts precise numbers on the draw angle engineering constraints and explains the physics behind each limit. Core rule: to successfully maintain the draw, to pull the fork inward, the draw angle must exceed the static friction coefficient of the two interacting materials. The coefficient of static friction for polished steel on synthetic ruby is approximately 0.16, corresponding to a friction angle of about 9 degrees. Critical limit: the absolute minimum draw angle for polished steel on synthetic ruby is approximately 9 degrees. Below this, the draw force cannot overcome the friction force at the contact point. A shock produces an inertial torque on the fork, and the net moment cannot return the fork to the banking pin. Optimal range, 13 to 16 degrees. This provides a 4-degree safety margin above the 9-degree friction limit, accounting for variations in lubrication, temperature, and manufacturing tolerances. The engineering trap at the bottom of this slide is the counterintuitive upper limit. Too large a draw angle above 16 degrees doesn't make the fork safer. It makes unlocking impossible. Here's why: a larger draw angle means a steeper inclination of the locking face. During unlocking, the balance must push the fork through the arc that slides the tooth off the locking face. A steeper inclination produces higher friction during This sliding motion. At some angle, the friction force becomes so large that the hairspring's restoring torque cannot overcome it. The tooth locks on the locking face. Watch stops. Rest face stoppage arrête sur le plan de repose. The draw angle has a floor set by shock protection and a ceiling set by unlocking. Friction. The 13 to 16 degree design range sits safely between both limits. This slide, The Microphysics of a Tick, is the synthesis conclusion for Part 2. It summarizes the complete four-phase sequence as a timeline and distills three core insights. Chronology, the timeline, a resting system is unlocked, gold bar, violently. Transfers energy, red bar, drops into safety, blue bar, and locks itself securely via draw physics. Four phases, four distinct characters, one repeating cycle. Geometry, approximately 30 degrees of active balance swing strictly dictates the entire four-phase sequence. That 30-degree roller arc is the fundamental geometric parameter. From it flows the 8-degree unlocking subarc, the 15 plus 15 symmetric impulse arc, the 1 to 2 degree drop, and the 30 arc minute to 1 degree lost motion. Everything derives from that single 30-degree window. Symmetry, the defining hallmark of the Swiss lever, preserving perfect isochronism. The 15 before, 15 after split about the dead point is the geometric guarantee that the escapement's energy injection produces no net frequency bias in the balance wheel. The teaser for Part 3, Control of Functions in the Mixed Layout, how watchmakers physically adjust and tune these microscopic angular margins. We've now described the ideal, correctly adjusted escapement in complete kinematic detail. In Part 3, we move to the practical question: how do you verify that an actual escapement is correctly adjusted, and what do you do when it isn't? The 7-step Ashevich procedure, the 3 plays, the 2 functional stoppages, and the geometric basis of the mixed layout. These are the tools that connect the theoretical ideal we've analyzed to the physical mechanism on the bench. Part 3 begins on the next slide. Welcome to Part 3, Control of Escapement Functions and the Mixed Layout. Covering sections 6.4 and 6.5. This part bridges theory to practice. The 6 topics on this slide define the structure of what we'll cover. Section 6.4.1, Plays and Clearances, less abats. Section 6.4.2, Shocks and Acoustics, less shocks. Section 6.4.3, The Reversal Defect, le renversement. Section 6.4.4, Functional Stoppages, less arrêts. Section 6.4.5, Finishing and Adjustment, l'achivage. And Section 6.5, The Mixed Layout, le trace mixed. The diagram on the right labels all the functional parts in both French and English: escape wheel, lever, entry and exit pallets, impulse pin, safety roller, guard pin, the dart, fork, balance wheel, hairspring. All labeled in their operational positions. Now, a word on the relationship between parts 1 through 3. Parts 1 and 2 gave you the anatomy and the ideal kinematics, what the correctly adjusted mechanism looks like in theory. Part 3 confronts the real world, even after careful manufacturing and assembly. Accumulated tolerances mean that most assembled escapements deviate from specification in at least some parameters. Part 3 gives you the framework to measure those deviations systematically and correct them. Everything in Part 3 assumes you have the Part 1 and Part 2 material in hand. The component names in both languages, the 4 kinematic phases, the angular values, and the draw geometry. Part 3 builds directly on all of that. Let's go. Section 6.4.1 introduces one of the most important practical concepts in escapement work, the abat, or play, and the master inequality that governs the 3 plays is on this slide in large font: abat de coin, less than abat de dard, less than abat de corne à l'extremite. Corner clearance, less than dart. Clearance, less than end of horn clearance. This inequality must be satisfied at all times, and violating it in either direction produces immediate malfunction. Core definition: an abat is the accidental angular travel the pallet fork can make from its banking pin position before a safety-critical contact occurs. Note: accidental, this is not normal operating travel. It's what happens when a shot displaces the fork. How far can it travel before something bad happens? 3 contacts define 3 plays, ordered from smallest to largest. Corner clearance, abat de coin. The inner corner of the fork mouth, where the entry wall meets the horn face, is the first dangerous contact point. If the fork displaces this far, the impulse pin strikes the corner in an uncontrolled way. Dart clearance, abat de dard. The dart tip contacts the solid circumference of the small roller. This is the primary safety intervention. The dart stops the fork before the horn corner can engage. End of horn clearance, abat de corne à l'extrémité. The outermost horn tip contacts the impulse pin. The outer safety limit. The tolerance principle: too large means catastrophic collision. Too small means binding and unreliable operation. Both are failures. The acceptable value for both horn and dart clearance is approximately 50% of the total engagement. Angle. This hierarchy is the complete safety architecture of the Swiss lever, expressed in 3 numbers and 1 inequality. Horn clearance, abat de corne, in engineering detail. This slide shows the 2 measurement zones clearly. Left diagram, normal clearance. Geometry. The abat de corne à l'extrémité is the clearance from the impulse pin to the outermost horn tip, the largest clearance value. The abat de coin is the clearance from the impulse pin to the inner corner where the fork mouth entry wall meets the horn face, the smallest value. Accepted value, approximately 50% of the total engagement angle. The total engagement angle is repose plus chemin perdu. At roughly half this value, the fork has a reasonable safety margin before the horn engages. The right diagram shows the maximum limit and the catastrophe. The red overlay shows what happens when horn clearance equals the full engagement angle. The fork displaces enough that an escape will tooth lands on the impulse face of the pallet stone rather than the locking face. When the impulse pin returns from the supplementary arc, the horn is now directly in its path. The horn traps the pin. The balance is stopped dead. Maximum limit: horn clearance must never equal or exceed the full engagement angle. This is absolute. Correction for excessive horn clearance: move the banking pins closer together. This reduces the total fork travel range, bringing the horns geometrically closer to the impulse pin in the rest position. Less room to move before the horn contacts the pin. Correction for insufficient horn clearance: move the banking pins further apart. More travel range, more clearance. Dart clearance, abat de dard, and its role as the primary protection mechanism. Definition: accidental fork travel from the banking pin until the safety dart contacts the outer circumference of the small roller. Accepted value: approximately 50% of the total engagement angle. The rule: abat de coin less than abat de dard less than abat de corne extremite. Let's understand the logic. If dart clearance were less than corner clearance, the horn corner would engage the impulse pin before the dart could activate. The dart's protective function would be bypassed. We want the dart to intervene. First, stopping the fork before the horn corner becomes relevant. So dart clearance must be greater than corner clearance. At the same time, dart clearance must be less than end of horn clearance. If it were larger, the horn tip would contact the impulse pin before the dart reached the roller, again bypassing the dart. The dart must be the first protection to activate. It sits in the middle of the safety hierarchy, and its specific value determines how much travel the fork can make before the primary protection kicks in. Warning limit: dart clearance must never equal or exceed the total engagement angle. If it did, the dart could potentially pass through the safety notch in the Small roller under shock conditions, finding no solid surface, and the fork would be free to travel to the reversal position. Complete safety bypass. Correction: if dart clearance is too large, the dart needs to be lengthened. If too small, shorten it carefully on a fine Arkansas stone, cleaning and deburring, measuring after each pass. Every single beat of a mechanical watch involves exactly 5 distinct mechanical impacts, 5 chocks occurring in the same chronological order every cycle, without exception. This slide shows all 5 in sequence. Shock 1: unlocking. The impulse pin strikes one wall of the fork mouth as it enters to begin the unlock. The softest shock, the relative velocity between pin and fork is low at initial contact. Shock 2: wheel impulse start. The escape wheel's locking tip strikes the impulse face of the pallet stone as the wheel begins to advance. More energetic, because the wheel has been accelerating under mainspring torque since it was freed. Shock 3: balance impulse start. The opposite wall of the fork mouth strikes the impulse pin as the fork reaches speed and begins driving the balance. This happens in rapid succession with shock 2. Shock 4: drop and landing. The escape wheel tooth falls through the drop angle and strikes the locking face of the opposite pallet stone. The loudest shock. La chute produces the highest amplitude acoustic signal of the cycle. Shock 5: lost motion in banking. The fork baguette strikes the banking pin as the draw force completes the fork's seating motion. The 3 principal shocks in decreasing order of intensity: drop loudest, impulse medium, unlocking softest. These 5 impacts produce the characteristic tick-tock sound of every mechanical watch. The relative timing and amplitude of these impacts, their acoustic signature, is what electronic timing instruments record as an oscillogram. Understanding which shock produces which sound is the foundation of acoustic escapement diagnostics. The oscillogram is the acoustic fingerprint of the escapement. And this slide shows what a healthy oscillogram looks like and how to read it. The instrument records sound pressure amplitude over time and displays it as a waveform. 3 distinct sound groups appear per complete tick-tock cycle. First sound: shock 1. The impulse pin touching the fork mouth at the start of unlocking. Smallest amplitude waveform on the left. A gentle contact at low relative velocity. Second sound: shocks 2 and 3 combined. The tooth impulse start and the balance impulse start occur in such rapid succession that most instruments merge them into a single waveform group. Medium amplitude. Third sound: shocks 4 and 5 combined. The tooth drop onto the pallet stone. Locking face, followed immediately by the baguette banking against the banking pin. Largest amplitude, the loudest event in the cycle. The relative timing between these 3 groups encodes diagnostic information. If the third sound is unusually loud compared to the second, it indicates excessive drop angle, the wheel falls too far before landing, dissipating more energy. If the timing between tick and tock is asymmetric, if they don't alternate evenly, it can indicate unequal entry and exit drops, or a beat error where the impulse pin is not centered in the fork mouth at the dead point. If the first sound is absent or very weak, it may indicate insufficient unlocking engagement, the pin is not making clean contact with the fork mouth wall. The oscillogram is used by timing machines that simultaneously measure rate, amplitude, and beat error. A trained watchmaker reading an oscillogram can often identify gross escapement faults without disassembly. Reversal renversement is one of the most critical and immediately destructive malfunctions of the Swiss lever escapement. The definition is precise. Reversal occurs when the impulse pin accidentally contacts the back revers of a fork horn instead of entering the fork mouth. The watch stops immediately. 2 distinct causes, shown in the 2 diagrams on this slide. Cause 1, bad assembly, mauvaise assemblage. When installing the balance wheel, if the impulse pin is positioned incorrectly relative to the fork, it enters from the wrong direction. Instead of descending into the open fork mouth, the pin Descends onto the outer face of a horn, the revers de corne, and is blocked. Balance stops. Fix, remove the balance, reposition the pallet fork against the correct banking pin, reinstall. Cause 2, shock displacement. A sudden external shock displaces the pallet fork from its resting position across to the opposite banking pin. With the fork now on the wrong side, the fork mouth is positioned away from the impulse pin's path of descent. When the balance returns, the impulse pin expects the fork mouth but encounters the horn revers instead. Watch stops. The safety dart is specifically designed to prevent cause 2 by physically blocking the fork's travel to less than the dart clearance angle. It prevents the fork from being displaced all the way to the reversal position. This is why correct dart clearance is so critical. If it exceeds the total engagement angle, the dart passes through the safety notch and the fork can reach the reversal position unchecked. Important distinction on the next slide: reversal is a failure of position. Rebat is a failure of energy. Different causes, completely different corrections. The anti-reversal protection of the Swiss lever uses 2 independent protective layers, defense and depth, so that failure of either one alone does not necessarily result in reversal. Primary protection, the safety dart, dart. During the supplementary arc, the dart tip runs against the solid outer circumference of the small roller. The dart clearance is less than the total engagement angle. Any shock displacing the fork is stopped by dart to roller contact after only the dart clearance angle of displacement. The fork cannot reach the reversal position because the solid roller is in the way. The dart can only pass freely through the roller during the impulse phase, when the safety notch encoche rotates to align with the dart's path. This alignment only occurs when the balance and fork are in the correct mutual position for a normal impulse event. Secondary protection, the guard horns, corns. Even if an unusual shock carries the dart into the notch at the wrong moment, the horns provide a second line of defense. Before the impulse pin can reach the horn revers, the front face of the pin contacts the inner face of the horn, stopping the fork with a less damaging contact geometry. The slide makes a critical distinction. Renversement, failure of position. The fork is displaced, the impulse pin hits the horn revers due to incorrect fork position. Instant stop. Rebat, failure of energy. The balance has excessive amplitude and swings so far that the impulse pin reaches the outermost extent of its arc and contacts the horn revers from the top. Caused by overimpulse, not shock displacement. Different root cause, completely different correction. Don't confuse them. Section 6.4.4 covers functional stoppages, less errors. 2 types, at opposite ends of the power reserve. This slide covers rest phase stoppage, arrêt sur le plan de repos. Definition: the escapement cannot complete the unlocking phase under the restoring force of the hairspring alone. A tooth is locked on the locking face. The balance is at one extreme of its swing, and the hairspring cannot push the fork hard enough to slide the tooth off the stone. The mechanical paradox highlighted on this slide: this condition is worst when the mainspring is fully wound, maximum torque. This is counterintuitive. You'd think maximum torque makes unlocking easier. But the opposite is true. Maximum mainspring torque produces maximum normal force of the tooth against the locking face. This maximum normal force produces maximum geometric recoil during unlocking. The tooth is being pushed backward harder. Maximum geometric recoil means maximum friction force during the unlocking slide, because friction equals normal force times friction coefficient. The hairspring must overcome all of this. Increased friction plus complete the geometric recoil, and at full wind it may not be able to. As the mainspring partially unwinds, torque decreases, normal force decreases. Friction during unlocking decreases, until the hairspring can overcome it. This is why a watch that stops when first wound but runs normally after a few hours Is exhibiting rest face stoppage. Engineering standards are strict. Large calibers, movement diameter above approximately 24 mm must never show rest face stoppage under any condition. Small format wristwatch calibers cannot completely avoid it at absolute full wind, but must be completely free of it after 24 hours of running. The complementary failure to rest face stoppage is impulse face stoppage. Arrêt sur le plan d'impulsion, where rest face stoppage is worst at full wind. Impulse face stoppage is the normal terminal event of every mechanical watch as it runs down. Definition: unlocking has successfully occurred, the tooth has been freed from the locking face, but the mainspring has insufficient remaining energy to drive the advancing tooth through the complete impulse phase. The tooth presses against the impulse face of the opposite pallet stone and cannot advance. The mechanism is stuck in a partially advanced equilibrium. Every watch will eventually reach this state as the power reserve depletes. The engineering question is not whether it will happen, but at what minimum power reserve level the watch self-restarts. The diagnostic procedure shown on this slide is specific and standardized. Step 1. Wind the mainspring exactly 2 to 3 ratchet teeth, 2 to 3 clicks of the crown. Step 2. Manually bring the balance to the impulse face stopped position using a pegwood stick to gently position it. Step 3. Hold the watch perfectly horizontal and wind very slowly, 1 ratchet click at a time, until the accumulated torque breaks the equilibrium and the watch restarts autonomously, without any physical assistance. Count the ratchet teeth wound from stopped position to self-start. That count is the minimum power reserve threshold. Acceptable restart standards: small format within 4 to 5 ratchet teeth, medium format within half a barrel turn, large format within 1 to 2 full barrel turns. If the watch requires more winding than these standards, the escapement efficiency is too low. Probable causes: worn pallet stones, incorrect drop angles, degraded or contaminated lubrication. Section 6.4.5 Elishevich. The watchmaker's master procedure for fine-tuning all escapement functions after assembly. The word comes from the French écrire, to complete, to perfect, and that's exactly what it means. Even after careful manufacturing and assembly, accumulated component tolerances can produce an assembled escapement that deviates from specification. Elishevich corrects this. 7 sequential steps. The sequence is not arbitrary, earlier steps are prerequisites for later steps. Working out of order produces false results. Step 1. Verify all 7 axial clearances, verifier les abats axiaux A through G. This is a vertical stack audit. All clearances between components along the balance staff axis and the pallet staff axis must be positive. No 2 components can contact each other axially under operating conditions or shock. The diagram shows the complete stack from plate to balance wheel, with each clearance labeled A through G. Clearance A, between the escape wheel and the pallet stones. Clearance B, between the dart boss plot and the main plate. Clearance C, between the fork top and the underside of the pallet bridge. Clearance D, between the dart tip and the underside of the small roller. Clearance E, between the fork mouth top and the underside of the large roller. Clearance F, between the small roller bottom and the lower jewel setting, chaton. Clearance G, between the impulse pin tip and the upper surface of the dart. All 7 must be positive and within specification. A negative clearance creates axial binding, parts grind against each other, causing timing irregularities that are difficult to diagnose without systematic checking. Correction: push the relevant jewel bearing deeper or shallower in its hole using appropriate staking tools under magnification. Continuing the vertical clearance audit, clearance B, dart to plate. Targeted zone, the axial gap between the safety dart or its boss, the plot, and the surface of the main plate directly below it. Technical verification: with the movement assembled, confirm that the dart assembly has vertical freedom without striking the plate. This clearance must be positive. Why it matters: if the dart boss is too long, or if the pallet staff jewels are set too shallow, the dart boss can contact the main plate during downward axial shock when the movement is jolted downward. This axial contact creates a binding force on the pallet fork, preventing normal operation for the duration of the shock and potentially damaging the staff pivots. Correction: push the pallet staff jewel bearings deeper into their holes by the appropriate amount, using the correct staking tools under the microscope, removing a few micrometers at a time and measuring after each adjustment. This clearance is part of the 7 clearance audit in Step 1 of achievage. All 7 must pass before proceeding to any functional checks. An insufficient axial clearance anywhere in the stack will cause erratic timing results in all subsequent tests, because the escapement intermittently binds in the vertical direction, especially under the shock conditions of the timing machine's test protocol. The systematic nature of Step 1, checking all 7 axial clearances before functional tests, is what makes it Step 1. It establishes a clean, binding-free baseline from which all subsequent measurements are valid. Clearance C, fork top to pallet bridge. Targeted zone, the gap between the top surface of the pallet fork body, decis de L anchor, and the underside of the pallet bridge, pont de anchor. Technical verification: measure the clearance between these two surfaces. The pallet fork must have vertical freedom to rotate about its pivot without the top of its body contacting the bridge above it. If this clearance is insufficient, the fork binds against the bridge during normal operation or under upward axial shock. Since the fork must rotate freely through its complete 10 to 13 degree travel on every beat, any periodic contact with the bridge interrupts the kinematic cycle, causing timing irregularities that are difficult to diagnose without systematic step-by-step checking. Correction: micro adjustments to the upper pallet staff jewel bearing, the jewel in the pallet bridge. Pushing this jewel bearing slightly deeper moves the pallet pivot lower, increasing the clearance between the fork top and the bridge underside. This is what the slide means by micro adjustments to the upper fork jewel bearing to maintain safe z-axis float. Each of the 7 clearances in Step 1 follows the same approach: identify which bearing controls the clearance, determine the direction of adjustment needed, and make micro adjustments under magnification, measuring after each pass. The target is a clearance that is positive enough vertical freedom to absorb shock, but not so large that the assortment stack becomes excessively loose. Clearance D, dart to small roller. Targeted zone, the clearance between the top surface of the safety dart and the underside of the small roller, decis du petit plateau. Technical verification: measure the vertical gap between the dart tip's upper surface and the rotating surface of the small roller beneath it. This clearance is critical for a specific reason: if it's insufficient, the rotating small roller will drag against the top of the safety dart during normal balance oscillation. The dart is fixed to the stationary pallet fork, the small roller spins with the balance staff at the balance wheel's oscillation frequency. Any contact between these two surfaces creates a continuous parasitic braking torque on the balance wheel, friction at every beat, in both directions, continuously dissipating the balance's kinetic energy. Consequence of insufficient clearance D, the balance runs at reduced amplitude. In severe cases, amplitude drops below the functional minimum and the watch stops or runs erratically. This is subtle because the effect is not a discrete event, it's a continuous small drain. It can be confused with a weak mainspring or a hairspring problem. Systematic verification of clearance D during achievage prevents this diagnostic ambiguity. Correction: adjust the lower balance staff jewel or the upper jewel in the main plate to move the roller assembly slightly away from the dart surface. A few micrometers of adjustment is typically sufficient. Clearance E, fork bottom to large roller. Targeted zone, the clearance between the top of the fork mouth and horns, the upper surface of the pallet fork, and the underside of the large roller. Decis du grand plateau. Technical verification: verify that the fork assembly and the large roller do not contact each other along the vertical axis during normal operation. This clearance ensures that the impulse pin can engage the fork mouth cleanly. The ruby pin descending into the fork mouth from above without the large roller disc itself scraping against the top of the fork body. If clearance E is insufficient, the flat underside of the grand plateau grinds against the top of the fork on every beat. Friction, wear, and timing irregularities result. The slide notes the corrective objective clearly: ensure the impulse pin can engage the fork cleanly without the two primary metallic planes scraping against one another. The two planes are the flat underside of the large roller and the flat top surface of the fork body. These must have a clean vertical gap. This is why the visual inspection of the complete assortment stack, looking at the cross-sectional profile from the side, is part of the initial assembly check before functional testing begins. If the stack is too tall in any zone, it becomes visible as insufficient vertical clearance and must be corrected before proceeding. Clearance F, small roller to jewel setting. Targeted zone, the clearance between the lowest surface of the small roller and the upper surface of the lower jewel setting, chaton inferior, in the main plate. Technical verification, measure the gap between the bottom of the petit plateau and the top of the balance staff lower bearing. This clearance prevents the rotating mass of the balance from grounding against the static chaton during extreme vertical shocks. Under a sharp downward impact, the balance staff and roller assembly move downward along the staff axis. If clearance F is 0 or negative, the small roller contacts the jewel setting and the balance staff is effectively jammed against the lower bearing. The balance stops oscillating until the shock passes and the staff returns to its normal axial position. In severe cases, repeated contact at this point can damage the lower pivot of the balance staff, one of the most delicate components in the movement, or crack the jewel setting itself. Correction: adjust the lower balance staff jewel bearing to increase the vertical distance between the chaton face and the small roller underside. Like all axial clearance corrections, done under magnification with staking tools, in very small increments. This clearance protects the most fragile component in the assortment, the lower balance staff pivot. Get it right before any functional testing begins. Clearance G, impulse pin tip to dart. Targeted zone, the clearance between the absolute tip of the ruby impulse pin, cheville de plateau, and the upper surface of the safety dart. Technical verification, measure the precise gap between the bottom of the impulse pin and the top of the dart. This is the final clearance in the 7-point axial audit, completing the vertical stack verification for the entire balance fork interface zone. The impulse pin projects downward from the large roller, the dart projects upward from the fork. These two components must never contact each other along the vertical axis during normal operation. If clearance G is insufficient, the tip of the impulse pin will strike the dart surface during each beat as the roller rotates. This jams the roller against the dart, stopping the balance wheel abruptly. The effect is a harsh, irregular beat with very low amplitude, potentially confused with a dirty pivot or a sticky hairspring without systematic diagnosis. The slide notes that clearance G completes the 7-step static vertical stack verification, ensuring all layers of the assortment float independently on the Z-axis. Think of it as a multi-layer sandwich of rotating and pivoting components, all stacked vertically, each layer requiring freedom from every adjacent layer. Once all 7 clearances are through G-pass verification, step 1 is complete. The stack is clear. Proceed to step 2, lateral impulse pin play in the fork mouth. Section 6.5, the mixed layout, Le Trace mixed. This is the geometric solution that has become the universal standard for Swiss lever escapements, and this slide explains both what it is and why it works. We've seen that equidistant rest gives symmetric unlocking but asymmetric impulse, and equidistant levers give symmetric impulse but asymmetric unlocking. The Fundamental dilemma: with fixed pallet stone geometry, you cannot simultaneously achieve perfect symmetry in both parameters. A trade-off is unavoidable. The mixed layout resolves this by deliberate compromise. Instead of placing the geometric reference point at the locking tip equidistant rest or at the impulse face midpoint equidistant levers, the mixed layout places it exactly midway between the two. Verification method, shown in the diagram: draw a circle centered on the fork. Pivot O with radius R. In the mixed layout, this circle passes midway between the sharp locking tip vector repose and the impulse face midpoint of each pallet stone simultaneously. That midpoint placement is the geometric definition of trace mixed. The result: a partial compensation of both asymmetries. The residual impulse. Asymmetry from moving away from equidistant levers partially cancels the residual. Unlocking asymmetry from moving away from equidistant rest. The two errors are of opposite sign, and in practice they largely offset each other. Status, as stated on the slide, used in virtually all modern Swiss lever escapements. This isn't a preference, it's the result of over a century of optimization converging on this geometric standard. The mixed layout is one of the most elegant examples of engineering optimization. In precision mechanics, achieving the best possible outcome within a fundamental constraint by finding the optimal position within it. This matrix puts all three layout geometries side by side for direct comparison. And it's the clearest summary of why trace mixed is the standard. Column 1, repose equidistance equidistant rest. Symmetric point, the locking tips, vex de repose. Unlocking difficulty, equal on both sides advantage. Impulse strength, stronger on the exit side due to a longer moment arm. Problem. Column 2, Levier's equidistance equidistant levers. Symmetric point, the impulse face midpoints. Unlocking difficulty, harder on the entry side problem. Impulse strength, equal on both sides advantage. Column 3, trace mixed, highlighted with a gold border as the standard. Symmetric point, midway between tip and midpoint. Unlocking difficulty, partially compensated. Impulse strength, partially compensated. Verdict: the remaining asymmetries offset one another, producing the most stable isochronism possible. This is the key insight. Neither asymmetry is eliminated, both still exist. But they're opposing asymmetries. The entry side is slightly harder to unlock, pulling the rate one way, and the exit side has slightly stronger impulse, pulling the rate the other way. These two residual errors partially cancel in the overall rate measurement. This cancellation is not perfect, but it's the best achievable with a fixed geometry pallet stone arrangement. More sophisticated solutions exist: silicon etched non-planar pallet faces, for example, but come with manufacturing complexity that makes them impractical for standard production. For examination purposes, know the three layouts, their symmetric points, their advantages, their weaknesses, and the reasoning for why trace mixed is adopted. This slide concludes part 3 with 4 synthesis statements that each capture a fundamental truth about the Swiss lever. First, static bounds. The escapement is governed by strict microscopic boundaries: ebat de coin less than ebat de dard less than ebat de corn. Violating these results in immediate stoppage. The plays are not guidelines. They are hard kinematic limits. Second, dynamic reality. The mechanism endures 5 distinct, chronologically sequenced shocks every cycle, generating the acoustic heartbeat of the watch. The tick-tock sound is not incidental. It is the physical evidence of 5 mechanical collisions happening 8 times per second in a watch beating at 4 Hz. Third, system safeguards. The elaborate geometry of darts and horns exists solely to prevent catastrophic reversals caused by physical shock. Every millimeter of horn shape, every micrometer of dart length, is specifically engineered to maintain the safety hierarchy under real-world wrist-wearing conditions. Fourth, the ultimate compromise. The trace mixed mathematically balances the unavoidable mechanical asymmetries, achieving the reliable timekeeping required of modern horology. Not by eliminating asymmetry, but by making opposing asymmetries cancel each other. Together, these four statements describe what the Swiss lever is: a precision mechanism that achieves its performance not through geometric perfection, because perfect geometry is physically impossible in a contact mechanism, but through intelligent, quantified compromise. Every measurement, every angle, every clearance is calibrated to extract the maximum precision from an inherently imperfect system. Part 4 now addresses how much power that system actually uses, and how efficiently it uses it. Welcome to Part 4, the final part of Chapter 6, covering sections 6.6 and 6.7. Power at the escape wheel and efficiency limits, followed by a survey of alternative escapement architectures. The main diagram on this slide shows the complete energy transfer cycle from barrel through to the balance wheel, with key formulas annotated. The input power formula, Pn equals tau times omega, torque times angular velocity. The efficiency formula, ETA equals P out divided by Pn, which equals 1 minus the friction and impact losses divided by Pn. The energy transfer chain at the top right: barrel, train, escape wheel, balance, regulation, and a feedback loop showing that the regulation output governs the timing of the distribution input. The escapement is in this feedback loop. It's both the output valve and the input controller. The loss comparison table in the lower left compares friction loss and impact loss between the Swiss lever and the detent escapement. The numbers tell a story. Wheel unpack in detail. The Swiss lever wastes more in friction, the detent has different loss characteristics, but both are dramatically less efficient than you might expect from a precision instrument. Part 4 addresses the energy economy of this system with precise numbers. What fraction of mainspring energy actually reaches the balance wheel? What are the loss mechanisms and can they be reduced? And how do alternative escapement types compare? These are engineering questions with quantitative answers, and the numbers are both impressive and humbling. Let's start with the energy chain. Section 6.6 begins with the energy chain and the 24-hour benchmark. This diagram traces the complete power flow from mainspring to balance wheel, with the loss mechanism at each stage labeled in red. Stage 1, the mainspring ressort de barrelet delivers total power P total. Stage 2, the barrel and gear train rouage transmit this power with efficiency of approximately 94%. 6% is lost to friction at gear, meshes and pivot bearings. Stage 3, the escape wheel receives the available power P are 24. Stage 4, the escapement delivers power to the balance wheel with an efficiency of approximately 30 to 41%. The remainder, 59 to 70%, is lost to friction, inertia, and shock. Stage 5, the balance wheel receives the delivered power PB that sustains its oscillation. Now, why use the 24-hour standard, PR24, rather than the maximum torque at full wind? The gold explanation box on the right answers clearly: a watch must maintain accuracy throughout a full day of wear. Mainspring torque drops as it unwinds. PR24 is the rigorous engineering baseline that proves sustained accurate oscillation, not just when freshly wound. If you designed the movement to run correctly only at maximum torque, it would slow down and eventually stop well before the power reserve was exhausted as the torque dropped below the minimum needed to sustain the balance's amplitude. Designing to PR24 ensures the movement continues to function correctly for at least 24 hours from full wind. This 24-hour baseline is the foundation for the power formula on the next slide. The power formula on this slide is the complete mathematical expression for PR24, the available power at the escape wheel after 24 hours of running. PR24 equals Mmax times the quantity 2 pi times ETA times beta times F, all, divided by ZE times rho. 6 parameters, each with a specific physical meaning. Mmax, maximum mainspring torque in Newton meters. The peak torque when fully wound. This is the starting energy density of the system. Eta, total mechanical efficiency of the gear train, approximately 0.94. About 6% of the barrel's power is lost to friction before reaching the escape wheel. Beta, the 24-hour torque rundown ratio, M24 divided by Mmax, approximately 0.8. After 24 hours of running, available torque is about 80% of maximum. This reflects the mainspring's characteristic discharge curve. F. Oscillator beat frequency in Hertz. A watch at 28,800 VPH has F equals 4 Hz. A watch at 18,000 VPH has F equals 2.5 Hz. ZE, number of teeth on the escape wheel. More teeth means fewer rotations per second for a given frequency, distributing power across more tooth advances. Rho, total gear ratio from barrel to escape pinion, the product of all gear ratios in the wheel set, typically several thousand to 1. The result, PR24, is in watts, typically in the range of 1 to 3 microwatts. For a standard wristwatch, this formula is the quantitative link between the mainspring specification and the escapement function. The movement designer uses it to verify sufficient power throughout the 24-hour operating window. Here is the most sobering number in all of watchmaking, the escapement efficiency ceiling. The formula is simple, ETAE equals PB divided by PR24. Power delivered to the balance, divided by power available at the escape wheel. What fraction of arriving power actually reaches the oscillator? 3 loss mechanisms consume the difference, labeled in the diagram. Mechanism 1, friction. Sliding contact between the escape wheel tooth and the ruby pallet stone impulse face during impulse. The dominant loss mechanism. The friction coefficient between hardened steel and synthetic ruby is approximately 0.10 to 0.15 for correctly lubricated contacts. Every sliding contact dissipates energy as heat. Mechanism 2, inertia. Every beat, the pallet fork accelerates from rest to full angular velocity and decelerates back to rest. The escape wheel accelerates through the drop and decelerates on landing. The kinetic energy in these moving parts is partially dissipated in the banking and drop impacts rather than recovered. Mechanism 3, shock dissipation. The 5 mechanical impacts per cycle convert kinetic energy directly into acoustic energy and heat. The drop shock alone dissipates a measurable fraction of total input power. The sum, even a perfectly adjusted, freshly lubricated Swiss lever escapement, wastes approximately 59 to 70% of the energy it receives. Only 30 to 41% reaches the balance wheel. This is not a manufacturing defect. It is a fundamental thermodynamic consequence of the mechanism's operating principle. Mechanical contact during each beat inevitably dissipates energy. To improve beyond this requires changing the contact geometry, the materials, or the fundamental mechanism. The efficiency ceiling is shown here as the FAR diagram, escapement efficiency. ETAE on the vertical axis against available power PR24 on the horizontal axis. The curve rises steeply at low power levels, where friction losses consume a disproportionately large fraction of small available power. As power increases, efficiency improves. Then the curve levels often plateaus asymptotically at approximately 41%. The specific reference point, at PR24 equal to 1.4 microwatts, efficiency reaches approximately 41%. Adding more power does not meaningfully improve efficiency beyond this ceiling. The 60% loss is structural. The statement at the bottom, even perfectly adjusted, the best Swiss lever escapements permanently waste 60 to 70% of input power. This severe energy limitation forces horological engineers to study historical and highly specialized alternative architectures. 5 improvement approaches are being pursued. First, reduce contact time, shorter Lift angles mean less sliding friction per beat. Second, minimize friction, silicon. Pallet stones and escape wheels have lower friction coefficients than ruby-on. Steel, require no lubrication, and maintain dimensions over millions of cycles without degradation. Third, minimize shock, optimizing drop angles and landing geometry. Fourth, lightweight moving parts, less mass means less kinetic energy to dissipate each beat. Fifth, constant force mechanisms, remontoirs decouple the escapement from gear train torque variations. Silicon escapements, introduced commercially in the early 2000s by Patek Philippe, Rolex, and Swatch Group under different trade names, have demonstrated efficiency improvements of 15 to 20% above the traditional ruby-on steel baseline. Section 6.7 presents the complete taxonomy of escapement types. This slide maps all 6 types will cover into the 3-class framework. Left zone in Class 1, recoil, the wheel is violently forced backward during the locking period. The verge escapement is the example. Constant recoil, no free arc, fundamentally incompatible with precision. Center zone in Class 2, frictional rest, permanent dragging contact on the oscillator throughout the supplementary arc. The cylinder escapement. The balance is never free from escapement friction. Right zone in Class 3, free, complete mechanical detachment during the supplementary arc. For types, the detent, the English lever, the pin pallet, and the Swiss lever. The small diagrams show the kinematic distinction between the 4, particularly the detent single impulse architecture versus the bilateral arrangement of the others. The guiding rule at the bottom, classification is strictly dictated by the behavior of the regulating organ during the supplementary arc. Class 1, the wheel reverses, fighting the oscillator. Class 2, the oscillator is in continuous contact with the escapement. Class 3, the oscillator is completely free. This classification is not about design style or historical period. It's about the physics of what happens to the oscillator during its nominal free arc. That physics determines precision capability. Classes 1 and 2 permanently violate the isolation requirement. Class 3 satisfies it. The detent escapement, échappement à détente, also called the chronometer escapement, is the most precise mechanical escapement ever designed for practical sustained use. This diagram shows its 5 key components, and the architecture is fundamentally different from the Swiss lever. The passing spring ressort d'or, labeled A, is an ultra-thin gold blade. Gold is chosen for its spring stiffness, fatigue resistance, non-magnetic properties, and corrosion resistance. This spring is the central operating element of the mechanism. The detent lame à ressort, B, is a pivoted lever that normally holds the escape wheel arrested via the locking pallet, pallet de verrouillage, C. The discharging pallet, pallet de dégagement, E, is mounted on the small roller and interacts with the passing spring during the descending arc. The impulse pallet, pallet d'impulsion, D, is mounted on the large roller and receives the direct impulse from the escape wheel tooth. Operating principle: during the descending arc, the discharging pallet contacts the passing spring and gently deflects it. This deflection moves the detent, lifting the locking pallet away from the arrested tooth. The escape wheel advances, the advancing tooth contacts the impulse pallet, and energy is delivered to the balance. During the ascending arc, the discharging pallet approaches the passing spring from the other direction. Now the spring simply yields, it bends out of the pallet's path without moving the detent at all. The escape wheel remains completely at rest throughout the entire ascending arc. Result: the balance is disturbed by escapement contact on only one alternation per complete oscillation. One disturbance per cycle instead of 2. This slide puts the detent's precision advantage in direct contrast with the Swiss lever. Left diagram: the descending arc, the discharging pallet trips the passing spring, the detent releases the escape wheel, the wheel advances, and the impulse pallet receives the direct drive. Impulse delivery occurs. Right diagram, the ascending arc, the discharging pallet bends the passing spring without tripping the detent. The detent stays locked. The escape wheel stays completely static, labeled static escape wheel. The balance swings through the complete ascending arc with zero escapement contact. The precision mandate at the bottom states the key comparison explicitly, unlike the Swiss lever, which disturbs the balance twice per cycle, tick, then tock. The detent delivers impulse on only one alternation, the descending arc result. One single disturbance per full oscillation cycle, versus two for the Swiss lever. Half as many perturbations. This reduced perturbation count, combined with the nearly zero force unlocking of the passing spring, gives the detent measurably superior isochronism under stable conditions. Marine chronometers with detent escapements routinely achieve daily rate accuracies of plus or minus a fraction of a second under stable conditions, comparable to the best quartz oscillators. But the cost is severe, highly susceptible to shock-induced tripping. A sharp jolt causes the detent to trip inadvertently, releasing the wheel at the wrong phase, and the chronometer stops. Requires manual resetting. This is why the detent is reserved exclusively for marine chronometers and precision bench instruments where the device is stabilized and protected from shock. Never wristwatches. The cylinder escapement échappement à cylindre belongs to a completely different philosophical family. There is no pallet fork at all. The assortment consists of only two components, the escape wheel and the cylinder. The cylinder itself is hollow, you can see the axial cross-section clearly in this diagram. It's a thin-walled tube of hardened steel with one side cut open to create a semicircular cross-section, approximately a half-pipe profile. This cylinder serves simultaneously as the balance staff and as the escapements locking and impulse element. The escape wheel has elevated triangular teeth, dense triangulaires élevis, projecting upward from the rim. As the cylinder and balance rotate, these elevated teeth alternately contact the outer surface of the cylinder wall outside rest repose exterior and enter the hollow interior for inside rest repose interior. During the transition from outside to inside, and vice versa, the inclined face of the triangular tooth slides against the cylinder lip, delivering an impulse to the cylinder and therefore to the balance. Since the balance staff is the escapement element, the escape wheel teeth are always in sliding contact with the cylinder walls. There is no free supplementary arc in the class 3 sense. This continuous contact classifies the cylinder as class 2 frictional rest. Advantage: an extremely low vertical profile, no separate pallet fork, no roller assembly. This made the cylinder dominant for ultra-flat pocket watches in the 18th and 19th centuries. Disadvantage: permanent friction on the oscillator, sensitivity to wear on the thin cylinder lips, and fundamentally limited isochronism. Superseded by the Swiss lever once precision became the primary requirement. The English lever escapement échappement à anchor anglais is the closest relative of the Swiss lever. Both are class 3 free escapements. Both use a pivoted pallet fork with two ruby stones. Both have a roller assembly with an impulse pin. Both have banking pins, a draw mechanism, guard horns. In terms of operating principle, mechanism architecture, and service procedure, they are essentially siblings. The single fundamental difference, shown clearly on this slide, is the escape wheel tooth geometry. Left diagram, Swiss geometry. The tooth has the heel shape, dent talon with a significant flat impulse face from B to C on the tooth itself. Both the tooth face and the pallet stone impulse face contribute to the sliding contact during impulse. Shared impulse, impulsion partigi. Right diagram, English geometry. The tooth is pointed, dent pointu tapering to a near sharp tip. The tooth presents essentially no flat impulse surface at the contact region. All the sliding inclined surface responsible for impulse must be on the pallet stone. The pallet stone does all the impulse work. Total impulse on. The pallet impulsion totale sur l'anchor. Kinematic consequence, English lever pallet stones must be significantly longer and more precisely profiled than Swiss lever stones, because they handle the complete energy transfer geometry without any tooth contribution. Longer stones are more exposed to wear and more difficult to manufacture. In practice, a small flat is typically left on the English tooth tip for robustness. A fully pointed tooth would wear too rapidly, but the impulse geometry remains dominated by the pallet stone face. For service, an English lever movement uses the same conceptual framework as the Swiss lever, with adjustments for the different stone geometry. The pin pallet escapement échappement à goupils is at the opposite end of the impulse distribution spectrum from the English lever. Where the English lever places all impulse on the pallet stone, the pin pallet places all impulse on the escape wheel tooth. The pallet stones are replaced by simple cylindrical steel pins, goupils and acier pressed into holes in the fork arms. Two steel cylinders acting as the pallets. Because cylindrical pins have no flat impulse face, they're round. All the impulse geometry must come from the escape wheel tooth. The teeth are wide, flat-faced, clog-shaped projections, dense sabot, specifically designed to provide the inclined impulse surface needed to push against the cylindrical pin and rotate the fork. Total impulse on the wheel, impulsion totale sur la roue. Manufacturing advantage, pressing cylindrical pins into drilled holes requires no precision stone setting technique, no shellac bonding, no micrometer level angular adjustment. Standard machining tolerances are sufficient. Production cost is dramatically lower than ruby stone designs. Engineering cost, the impulse geometry is less precise because a cylinder's convex surface provides an imprecisely defined contact zone against the flat tooth face. Accuracy is lower. Friction between steel pin and steel tooth face is higher than ruby on steel. Wear progresses more rapidly. Classification, despite the simplified construction, the pin pallet is still class 3 free. During the supplementary arc, the fork clears the balance roller completely. The lower accuracy comes from less precise impulse geometry and higher friction, not from loss of oscillator freedom. Typical applications: alarm clocks, travel clocks, inexpensive mechanical timepieces where cost constraints dominate. The verge escapement échappement à verge, also called the crown wheel. Escapement échappement à roue de rencontre is the oldest mechanical escapement in the historical record. The architecture is entirely different from anything we've covered. There is no separate pallet fork. The escape wheel roue de rencontre rotates in a plane, but its teeth project radially outward and perpendicular to the rotation plane, like the points of a crown. The balance staff, the verge itself, runs perpendicular to the crown wheels rotation axis. Two flat metal plates, the pallets or flags, are mounted on the verge at approximately 90 degrees to each other. Each flag catches teeth on opposite sides of the crown wheel as it rotates. Operation: a crown wheel tooth strikes the upper flag and pushes it, rotating the verge in balance. The balance continues swinging until the lower flag engages a tooth on the other side of the crown wheel, stopping it, momentarily driving it backward under the balance's kinetic energy, then receiving impulse in the return direction. There is no supplementary arc. The crown wheel is always in contact with one flag or the other. Every beat involves recoil. Class 1 in its purest historical form. Kinematic consequence: the balance wheel's effective restoring force is the hairspring torque minus the variable recoil force from the gear train. This changes continuously with the mainspring state of discharge. Perfect isochronism is mathematically impossible. Historical significance: the verge was revolutionary. It enabled the first self-sustaining mechanical clocks from the 13th century onward. By modern standards, entirely unsuitable for precision timekeeping, but without it, there would be no modern horology. It is the ancestor of every mechanical timekeeper that exists. This slide shows the complete spectrum of impulse distribution across the three lever-type Class 3 escapements, and it clarifies precisely why the Swiss lever occupies the dominant position it does. The spectrum is defined by where the impulse surface is located. At the left extreme, the pin pallet 100% on the wheel. The sabot tooths flat face does all the work. The cylindrical pin is purely passive. At the right extreme, the English lever 100% on the pallet. The pointed tooth acts only as a driver. The long ruby pallet face carries the entire impulse. Geometry. At the center, the Swiss lever shared impulse, impulsion partige. The tooths inclined impulse face B to C, and the ruby pallet stone's impulse face, both contribute approximately equally to energy transfer. The engineering insight at the bottom, this continuum encapsulates why the Swiss lever is the universal standard. It is a deliberate, optimized geometric compromise that shares the sliding friction and kinetic wear between two highly specialized, polished planes, maximizing component lifespan and reliability. The Swiss lever distributes wear between two high-quality polished surfaces. Hardened steel tooth face and synthetic ruby stone face rather than concentrating it entirely on one. The total friction is split. The wear rate at each surface is halved. The pallet stones are shorter and more robust than English lever stones because they only need to provide half the impulse geometry. The tooth profile is simpler and more durable than the English clogged tooth. Shared impulse is the best total solution for durability, precision, and manufacturing consistency. This is the master comparison table, tableau comparatif de tous les échappements. Your complete reference for all 6 escapement types in Chapter 6. Swiss lever, Class 3 free. Key feature, shared impulse, fork plus roller. Impulse location, shared between tooth and pallet. Accuracy, very high. Use all modern mechanical watches. Detent, Class 3 free. Key feature, single impulse per cycle, passing spring. Ressort de passage. Impulse location, on the impulse pallet. Accuracy, highest. Use, marine chronometers only. English lever, Class 3 free. Key feature, pointed teeth, dense pointures. Impulse location, total impulse on pallet, impulsion totale sur l'anchor. Accuracy, high. Use, antique pocket watches. Pin pallet, Class 3 free. Key feature, steel pins as pallets. Impulse location. Total impulse on wheel, impulsion totale sur la roue. Accuracy, moderate. Use, alarm clocks. Cylinder, Class 2 frictional rest. Key feature, no fork, cylinder equals balance. Staff. Impulse location, shared between tooth and cylinder lips. Accuracy, low to moderate. Use, antique flat pocket watches. Verge, Class 1 recoil. Key feature, constant recoil, crown wheel roue de rencontre. Impulse location, direct tooth contact. Accuracy, low. Use, pre-1700s. Clocks. Study this table in both English and French until you can reproduce it from memory. Examination questions frequently test this comparative knowledge, not just the properties of the Swiss lever alone, but its position within the broader taxonomy. Where does each type fall in the 3-class system? What is the impulse distribution? What accuracy class does it achieve? This slide shows the physics of why classes 1 and 2 are fundamentally inadequate for precision timekeeping, presented as force over time diagrams for each class. Left diagram, Class 3, free escapement. The horizontal line represents the parasitic force on the oscillator during the supplementary arc flat at 0. Delta E equals 0. The regulating organ is entirely undisturbed. Isochronism is mathematically perfect during the free arc. Center diagram, Class 2, frictional rest. During the supplementary arc, the Oscillator is in continuous contact with the escape wheel via the cylinder walls. The orange noise band represents continuous frictional drag, a parasitic braking force that decreases as the mainspring unwinds. The balance's effective restoring force shifts continuously with every tick. Isochronism is permanently degraded. Right diagram, Class 1, recoil. The violet-red spikes are the negative kinetic vectors, vector cinetique negative. During what should be the supplementary arc, the gear train is being driven backward, fighting directly against the balances natural oscillation frequency. The magnitude of that recoil force changes continuously with the mainspring's state of discharge. The result is unambiguous, perfect isochronism is structurally impossible. The conclusion box at the bottom of the slide summarizes everything in one statement: modern precision requires absolute isolation of the regulating organ. And classes 1 and 2 permanently violate this physical law. Not occasionally. Not under extreme conditions. Permanently, by design, on every single beat. This is why the classification system is not historical trivia. It is a direct statement about what a given escapement can and cannot achieve in terms of precision, regardless of how well it is manufactured or adjusted. This slide presents the mandate for precision in free escapements and the engineering trade-off that defines the difference between the two most important Class 3 designs. The golden rule at the top: the regulating organ must remain undisturbed for the maximum possible duration of its supplementary arc. This is the single overriding principle from which all Class 3 escapement engineering flows. Left panel, the theoretical ideal: 0 disturbances per cycle. If you could build an escapement that injected energy into the balance with 0 physical contact, like wireless charging, the balance would oscillate in mathematically perfect isochronism forever, governed only by its own moment of inertia and hairspring stiffness. This is the target. It is also, as the slide states, physically impossible in any mechanical system that must transfer energy through contact. Right panel, the engineering trade-off. 2 real-world solutions, side by side. Option A, the detent reality, achieves 1 disturbance per cycle. The balance is contacted only on the descending arc. This yields maximum precision. But it permanently sacrifices safety. The passing spring is catastrophically vulnerable to shock-induced tripping. 1 sharp jolt and the chronometer stops. Option B, the Swiss lever reality, accepts 2 disturbances per cycle, 1 on each alternation. This costs some precision relative to the detent. But those 2 disturbances per cycle are what allows the integration of the draw mechanism, the safety dart, and the guard horns, the complete shock protection architecture that makes wristwatch use possible. The Swiss lever is not a compromise in the pejorative sense. It is a deliberate, quantified engineering decision, accepting 2 disturbances per cycle to gain robust, reliable, wrist-proof safety. Every gram of that decision is justified by 150 years of successful wristwatch production. Here is the definitive answer to the question: why does the Swiss lever dominate mechanical watchmaking? This radar chart and the accompanying analysis panel give you the complete picture. The radar chart has 4 axes: precision at the top, robustness on the left, efficiency on the right, and safety at the bottom. Look at shape 2, the detent, shown in orange. It spikes at precision. Extreme precision, as high as any mechanical escapement has ever achieved. But look at safety, it scores nearly 0. Robustness, nearly 0. The detent is a precision instrument that cannot survive real-world conditions. Now look at the Swiss lever, the blue quadrilateral. Not maximum on any single axis, but balanced across all 4. Solid precision. High robustness. Good safety. Moderate efficiency. A stable, balanced shape. The Triumphs panel on the right makes the case explicitly. The Swiss lever guarantees class 3 freedom. The balance is completely isolated during the supplementary arc. It delivers perfectly symmetric impulse via the mixed layout, splitting positional error equally about the dead point. It actively uses the draw for persistent shock resistance, the mainspring's own energy, holds the fork against the banking pin, and it physically prevents catastrophic reversals via the safety dart and guard horn system. The accepted costs panel is equally honest. The Swiss lever suffers approximately 60% power loss unavoidable under the current mechanism. It endures 5 violent kinetic shocks per cycle. And it produces two-sided disturbance of the balance, one on each alternation. The conclusion at the bottom of the slide is the most important single sentence. In this entire chapter, it is not the most precise escapement ever invented. It is the most reliable precision escapement ever invented. That distinction is everything. Precision on the bench and precision on the wrist are completely different engineering specifications. The Swiss lever solves both simultaneously, and that is why it dominates. This is the master knowledge map for sections 6.1 through 6.3, the first half of chapter 6, and it gives you the complete structural overview of everything we've covered in parts 1 and 2. The tree branches from chapter 6, escapements, into 3 sections. Section 6.1, generalities, 3 core deliverables. First, the definition. The escapement is a distributor organ, the link between the regulating organ and the gear train, performing 2 simultaneous functions, distributing energy and counting time. Second, the energy chain, spring, barrel, train, escapement. Regulation, display, with the escapement highlighted as the critical control point between transmission and regulation. Third, the 3-class system. Class 1 recoil, Class 2 frictional rest, Class 3 free, defined by the behavior of the oscillator during the supplementary arc. Section 6.2, components, 4 core deliverables. The assortment of 19 named parts across 3 subassemblies. The geometry of the heel-shaped tooth with locking face AB and impulse face BC, and the pallet stone with points through F, with a layout of the 3 centers as pointage, inline versus angled. And the limitation methods, ettocox for production, goupils for adjustment. Section 6.3, functions, 3 core deliverables. The 4 kinematic phases. Repose, degagement, impulsion, sécurité. The key angular values for each component in each phase, supplementary arc 220 to 270 degrees, unlocking 8 degrees roller, impulse 30 degrees symmetric about the dead point, fork 10 degrees, will 10 degrees 30 arc minutes, drop 1 to 2 degrees. And the draw physics, beta equals alpha plus epsilon for entry, alpha minus epsilon for exit, optimal range 13 to 16 degrees. Study this map until you can reconstruct it from memory. Every branch represents a category of examination question. This is the master knowledge map for sections 6.4 through 6.7, the second half of chapter 6, completing the full chapter architecture. Section 6.4, control, 5 subtopics displayed as branches. 3 clearances, the master inequality abat de coin less than abat de dard. Less than abat de corn, each approximately 50% of the total engagement. Angle. Violating this hierarchy causes immediate stoppage. The 5 shock sequence, unlocking, will impulse start, balance impulse start. Drop, the loudest, and banking. 3 sound groups for oscillogram analysis. System failures, renversement versus rebat, failure of position versus failure of energy, different causes, different corrections. Primary protection via the dart, secondary via the horns. Stoppages, rest phase stoppage worst at full wind, forbidden for large calibers. Impulse phase stoppage unavoidable at power reserve end, with specific restart. Standards by caliber size. The 7-step achievage, axial clearance is a through G, lateral play, horn clearance. Dart clearance, rest engagement, drop equalization, and lost motion, in that order, every time. Section 6.5, Layout, 1 core deliverable, the trace mixed as the optimal. Geometric compromise between equidistant rest and equidistant levers. The remaining asymmetries cancel each other out in practice. Section 6.6, Power, 3 core deliverables, the PR24 formula with 6 parameters, the 41% efficiency ceiling driven by friction, inertia, and shock dissipation, and NIHS 34-04 balance selection by moment of inertia versus available power. Section 6.7, Alternatives, the taxonomy of 5 alternative types, detent, English lever, pin pallet, cylinder, and verge. The impulse distribution spectrum from total on wheel through shared to total on pallet. The free escapement mandate that classes 1 and 2 permanently violate. And the ultimate conclusion, the Swiss lever is not the most precise, but it is the most reliable precision escapement ever made. Chapter 6, Final Summary. This slide gives you the 4 essential principles that every master watchmaker must internalize, not as memorized rules, but as deeply understood engineering truths. Principle 1, Isolate the oscillator. Minimize contact time, protect the supplementary arc. The entire design philosophy of the Swiss lever, and of every Class 3 free escapement, reduces to this single mandate. Every microsecond the balance spends in contact with the escapement is a microsecond of potential frequency error. Every microsecond it spends free is a microsecond of perfect isochronism. The ratio of supplementary arc to lift angle is the single most important parameter in escapement design, and maximizing it is the engine of every major advance in horological precision. Principle 2, Ensure safety. The draw angle must strictly exceed the friction angle, greater than 9 degrees for ruby on steel. Below this minimum, any shock can displace the fork and cause a reversal. Above the maximum of 16 degrees, unlocking becomes mechanically impossible. The 13 to 16 degree design range is the narrow corridor between 2 catastrophic failure modes, and operating within it is non-negotiable. Principle 3, Manage the clearances. Ebat de coin less than ebat de dard. Less than ebat de corn. Violate this, and the watch stops. This is not a guideline. It is a hard kinematic constraint that the mechanism enforces absolutely, on every single beat. Principle 4, Embrace compromise. The trace mixed and the Swiss lever endure mechanical violence and energy loss, 60 to 70% of input power wasted every cycle, to guarantee unmatched reliability under real-world conditions. The escapement is the energy distributor and the time counter. Its fundamental challenge, wasting 60 to 70% of available energy, is precisely what motivates every modern advance in horological material science: silicon components, constant force mechanisms, optimized geometry. The loss is not a failure. It is the engineering problem that the next generation of horology is built to solve. End of Chapter 6. End of Course Module, Théorie Horlogère.